Good morning. This is a video on importance of codes and standards for products which are for the critical applications and how to understand codes and standards and how to form different steps while executing this kind of projects. So it is explained in the next two slides. In continuation of our slide, just expand what is code, and one of the if you really see ODE try to explain related to the fabrication industry, it could be conformance of detailed engineering. When we receive order, we try to do the detailed engineering. Or detailed engineering may be a detailing of design, detailing of manufacturing, detailing of testing, detailing of overall the acceptance standard for the product or the part, and it could be the final documentation and the way the documentation will be submitted. How do we really differentiate ourselves with the rest of the manufacturing teams or the fabricators? Since we are in the fabrication industry and manufacturing industry, and these two industries are going to grow in the coming days, let's understand what is a good engineering practice. When we say that there are minimum requirements are given in the code, the customer specifies his requirements, but when we are trying to meet those customer requirements or the minimum requirements, I think today's quality standards have improved to such an extent that everybody is meeting these requirements or expectations. So we need to do something more. Now, something more need not be in terms of high standards of quality, because finally it has to be a competitive product. So you cannot really get moon for everything. But what we are following, is it having a consistency? Is it a repeatable process? Can the end product be estimated or end product be predicted? So good engineering is a good methoding, or it's following almost 100% of the standard or the code. And to do that, we have to have very efficient and cost effective processes which will offer the solution for that process. And it should also meet the operational, safety and regulatory requirements. Hi friends, this is Surendra Vaidya. I am going to talk today to you about the manufacturing etiquettes or project execution etiquettes or good practices in executing projects. This particular topic is very important for all of us, as most of our product development today is happening to certain codes or specifications or some ratings or the emblems or the certification logos which are required to be put on our products. Every person who is going to be the end user is worried about what is the safety, how this particular equipment or the product has been designed, how it has been manufactured, and how it has been certified. Having a good concept is very important, but so also the overall execution process till the time product reaches the end user or the ultimate customer. So mind to market is one of the jargon which is used by most of the management gurus, and I'm not going to elaborate the complete chain, but let's take example of any fabricated item or any item which we are designing it for aerospace or defense, or any item which we are going to use it for our machinery, appliances, or we are going to use it in chemical industry, food industry. So anywhere we are going to use the end application of this product or the service, how are we going to execute it? So as I said earlier, that there are always some codes, specifications, standards to which we try to manufacture, or we try to design, or we try to conceptualize a product, and also get it into a physical hardware where we can get the benefit of having that product with us. So as you see here, what are codes? Codes are crucial for fabrication of critical equipments. Now, if you are talking about nuclear equipment, aerospace equipments, defense equipments, chemical industry equipments, they can be treated as critical equipments. It is not that the other equipments are not critical, but within the operating parameters, the service conditions, the serviceability of these, the taking a downtime on these equipments or appliances needs to be considered. We need to ensure safety, we need to ensure reliability of these products. The reliability basically comes in through the quality control, through the design safety factors, and if we are using a proven specification or a code where we have a reference of earlier products when they have undergone a similar kind of a treatment, have worked to its life cycle. The efficiency, the most important part in today's world. Everything has to be efficient. It has to be energy efficient. It has to be process wise, it has to be efficient. The losses should be as low as possible. And to establish that, there has to be a minimum standard. And the minimum standard comes in by having the best practices for design, for selection of material, the fabrication processes. Specifications are something which are over and above. The standards and specifications are something which are over and above the code, and they are very specific to that particular product. A code which can be for structural fabrication, let's say a bridge, or let's say a tower, or let's say a building which is constructed out of a steel fabrication. And we also have structures at home, like we have the storage racks, we have the cupboards, we have so many other utilities like tables and chairs. They all are structurally designed. So there is a minimum code of what materials normally one can use in structural welding, and how that material strength wise, its behavior, what kind of a protection is required on these structures, whether you have to give a red oxide, whether you have to do a galvanizing, whether you have to do a powder coating, which is the best method in the given environment. And then the standards will tell about very specific. If it is a chair, what kind of a comfort is required in that chair, what kind of a aesthetic value it should have in that chair, what kind of full proofing as far as the safety is concerned in that. So these are all going to be, may not be applicable for a bridge or for a building construction, but those are required for table and chair. So like that, there is a difference between code and standard, and it is very essential for all of us to read these code and standards. At least one person in the organization must read these code standards, and whatever is applicable to the various departments, for design, for material selection, for procurement, for fabrication, for NDT, for heat treatment, for surface treatments, for painting, that must be passed on to the respective experts or respective supervisors to understand the code requirements or the standard requirements, and then decide for ourselves what are the good or the best practices I will choose to ensure that I meet the minimum requirements of codes, and also put beyond the code based on my experience or the organizational experience into it. So the codes and standards will help us in ensuring safety. The codes and standards will help us in achieving the consistency and the reliability, because all this data what we are collecting or gathering or discussing is converted into the design and the notes on the drawings, or there could be an attachment to the design documentation which will specify all the discussions what we have. And in our next slide we are going to see that as to what is the one of the recommended sequence for design to execution. Then there are certain regulatory requirements, like if you are making a boiler, then there is an Indian Boiler Regulation, IBR, or if you are making any vehicle, then there are certain norms which are given in Bharat 3, Bharat 4, now we are on Bharat 6. The C rating for our appliances, that gives what are the regulatory requirements. For example, if it is a electrical appliance, then what kind of a voltage it will be suited to. The voltage in each country may vary to some extent. It can be from 210 for a single phase to maybe 240, 250 in most of the European and Asian countries, whereas in America they follow 110 volts. So this is a regulatory requirement which comes in there. America follows 60 hertz, whereas most of the rest of the world you will see 50 hertz frequency which is used on the alternating current. Then there are certain requirements as to what material you can use and what material you cannot use, or if you have any disposal. So when the spares are going to be replaced, the parts which have a limited lifetime, then how to dispose of them. So how to design this so that you can easily remove and fix it, and the bare minimum portion of that is removed and fixed. And last, the code also looks for innovating with a strong base. That means when you are going to do any modifications, or you improve or you innovate a process, you shall write back to the code or the standards committee and inform them that this is a new alloy which gives this kind of a properties, or this is a new heat treatment which guarantees the heat treated properties, or this is a new design concept which we have brought in, which is giving more reliability or it is giving more consistency in our product, and that requires to be incorporated in future revisions to codes and standards, so that we will get it properly documented, and also document it every time we create a new product, a new process, a new technology, or a new norm or acceptance criteria when we are going to do NDT or physical property testing. Now, what are the recommended practices? Let's go to the next slide. Now, the steps to be followed. Now, this is not the only process which can be followed. There could be variations from product to product, but in a generalized condition, when we say mind to market, the concept which is there in the designer's mind, he tries to put it down on paper or nowadays on computer and on screen, and he tries to explain to his colleagues from various other departments as to how the product will look like, what specifications, what kind of a construction details are likely to come in this particular product. So this is called as a general assembly drawing. Now this is a very, very important step. Even though it is a general assembly drawing and not the final product, we need to really worry about it, and the team members shall have the discussions on the possible tolerances which it is going to emerge, the possible materials it is going to emerge based on a general assembly drawing, which gives the idea of designer or what is there in his mind and how it is going to get converted into a reality. So the capabilities, and then to establish that we really have this capability, we can do some tryouts, qualifications to validate and give back data to the designer, as if you are going to choose these materials, then these are the likely properties I can achieve in the manufacturing processes. After welding, after heat treatment, after machining, and what are the likely distortions and the tolerances I am likely to achieve. Maybe a particular surface requires a very high hardness, but we don't have that kind of a facility to harden it or machine it or grind it. Then what kind of a sequence are we going to invest? Are we going to subcontract? Are we going to vendor out these operations? And then does vendor has the capability and understanding of our requirements? So those are required to be discussed and found out. So the first meeting happens with the manufacturing and the project management and the procurement team to understand the design concept, probable materials, probable processes, probable tolerances, probable NDT, and then each one gives his feedback or the comfort or the efforts which are required for the selected idea or a design. A similar exercise is carried out by the QA team, NDT team. They decide at what stage the inspection is best done, at what stage NDT is best done, and if there are third party or customer inspection stages, those are also identified to ensure that this is where the design has to take a pause and ensure that we conduct and satisfy customer or customer representatives or the third party at that. Yes, so we'll move further, and the next step is to have a cross-functional team to understand the flow of activities. Now, individually or in the smaller groups, it has been discussed to understand what is there with the designer's mind and how he is going to convert that into a drawing and the specifications or the notes on that. Now, each one, whatever has been understood, that is going to be talked in a cross-functional team where the entire flow of activities, the way they are going to happen, they will be putting in that sequence their own views or their own ideas as to how we are going to convert the GAD into a R0 version. To do that, we need to prepare a flow chart, flow of activities, and note here most important activity. What in the second and the third bullet we discussed was individual for that particular process or for only for that activity. Now we have not discussed in that for the previous activities output is going to be the input for the subsequent activities, and this internal customer kind of a relationship is going to exist, a supplier and a customer, between the processes which are being properly sequenced, and therefore there has to be a handshake between the two boxes or the two processes which are consecutive, and then only we will be able to really meet the tolerances. There are certain specs or tolerances are best achieved by the process itself, not by the external. So a machining may have some idea to hold that particular job, and we don't require external fixture or any other constraint, whereas the machine has a special chuck, or machine has a special tool, or machine has a special feature, one more axis, wherein we can utilize this particular aspect of the machine for controlling or maintaining our dimensions. Similarly, by using different techniques in welding, or by selection of the right processes, or by selection of the right edge preparation for the welding, or by sequencing certain activities of welding and then machining and then heat treatment and then welding, we may be able to achieve the tolerances, but there each of the process owner has to clearly outline as to what he will do when the job will come to his department, and how he is trying to manage the best possible results from his process or from his own. But there could be some deliberate pre-cambers or deliberate distortions or deliberate material removal or keeping it extra will be maintained based on our experience and certain data what we have discussed in second and third point, based on some tryouts or based on some mock-ups. Then the design is going to sum up all the discussions what we had so far into R0 version, and with the inputs of everyone this version will get ready. But now a cross-functional team, once again all the stakeholders in execution of this particular project, they will sit and do a preliminary design review. So from general assembly drawing, now we have come up to preliminary design review. Now this is a place where process failure mode analysis, that means now we have selected the processes, we have selected the material, we have listed down all the special applicable notes, and a formal design with dimensions, tolerances and all other critical data has been now specified. So while using an execution, if we can identify what can go wrong in the selected processes, Then the monitoring or taking care or being ready if in case that situation occurs, how are we going to rectify or how are we going to take the further steps. Now with this we will be coming to a CDR. After PDR, after having done PFMEA, we will be doing the critical design review. It means now everything is frozen, qualifications are done, tryouts are done, achieving properties, tolerances or hardness or after heat treatment, whatever are the distortion levels or the fixtures, everything has been now frozen, and we are now ready to launch our first article. So when the first article gets produced, the inspection report of the first article gets into the CDR, the critical design review, and if there we are getting all the requirements which are meeting the specs and codes and customer expectations and the end users expectations, then the CDR is also approved. Once you have a CDR, then you can really run and further optimize this process without changing the essential and non-essential variables, and then create a PERT chart and adhere it while you are into the production mode. So this is the importance of codes, standards and the various steps to be followed. Any shortcut in this will create a havoc while execution, while the jobs or the parts or the assemblies are on the shop floor, and once the job is kicked off on the shop floor, then we cannot wait. It's very costly as it occupies the floor area, it occupies the volume, the space, the storage materials, it always in front of you. So even if you are stopped working for some reason, the reason for the stoppage keeps on bothering you, and as a result the overall efficiency comes down. So it is good to spend more time before we go to PDR, before we go to CDR, and once the CDR is approved and your PERT chart is approved, I think it is very easy for us to execute it seamless, smooth and in a very effective, most efficient manner, and so that we can adhere to our PERT, whatever timelines we have outlined. And it also gives the interconnectivity, interdependency on each part, sub-assemblies, assemblies and the final product. And the buffer, as you know, we keep it only at the end. All other buffers are required to be absorbed any delays by improving the processes, by deploying more resources, so that only at the end we have sufficient time or a buffer to conduct a recovery. I hope this teaser on codes, standards, specifications and its importance and the steps to be followed is liked by you, and we can discuss this into more details in each aspect of the code as it has been specified in the earlier slide. So how it gives a criteria for design, how it gives criteria for manufacturing, then what are all the supplementary or the codes which are required to be read in conjunction with the other codes and standards, and overall how are we going to understand each code, whether it is for consumables, whether it is for machinery, whether it is for infrastructure, whether it is for manufacturing, whether it is for personal qualifications, process qualifications, facility qualifications, or instrument qualifications, or the design criterias, what formulas are we going to use, what considerations are we going to give for the external conditions and the worst conditions in which a customer or a product is likely to be handled, and then how are we going to still keep on improving our good practices in manufacturing so that ultimately our product is safe, it delivers the intended purpose, customer gets what he wants or beyond what he wants, and we get the repeat orders or we get the futuristic orders. So let's meet and discuss it further. Thank you. Now let's see the role of a welding engineer in manufacturing. As we understand that welding is the most important process in any manufacturing, as it joins two parts together, and while joining these two parts together we are going to heat melt the material and bring them together with a welding consumable, which is another alloy, which could be a third alloy if the two parts which are getting joined are of the same material but may not be from the same heat or may not be from the same manufacturing process. One could be a rolled product, one could be a cast product, one could be a forged product, one could be heavily machined product, one could be heavily formed product, or both could be with all these complications and different materials, different metallurgies. And to join them, then we'll have to use another metallurgy or a combination of alloys by which we will be able to bring these two parts together and give them the required strength and the soundness. So the first, I think the role of a welding engineer is to really understand the physics. Now, what we mean by physics, whether it is a structure, is it a pressure vessel, is it a reactor, a heat exchanger, what is the end use, what is the purpose of this particular equipment, what it is going to really operate for, and for what is the intended service applications and the service lifetime. Second is how it has been engineered. We have choices of materials, we have choices of designs, we have choices of constructions. So which of this choice has been selected, and have we done the fine tuning of each and every part, assembly, testing sequence to get us the best and effective solution, as we saw in our first or the second slide. Then comes the metallurgy. Now after having engineered, that means the material of construction is now decided, so we understand whether the part is made with carbon steel, stainless steel, nickel based alloys, cobalt based alloys, aluminium, or is it a titanium or any other alloy like tungsten and all. Then comes in the metallurgy we understand also not only the alloy, but we also understand how it is given a shape and what could be the end result of manufacturing this product in that particular fashion. So this will tell us the grain size, the corrosion properties, the impact properties, the sluggishness of this material, the fluidity of this material, can that be worked in different positions. And then comes the material, where the formability, and then machinability, and then comes the welding, whether this alloy can be easily welded, or what are all the best options to weld this. The second is to meet the structural requirements. If it is a bridge, you need to have what are the structural rigidity of these parts. So accordingly, the joints, the trusses, the overlap, joining of materials is being decided. The process, it can be a carbon steel with stainless steel overlay to get a corrosion resistance. It can be alloy steel with suitable heat treatment to achieve higher hardness or strength. Then there are regulatory, safety, environmental requirements. A regulatory requirement will be that for a boiler, it cannot be heated beyond 400 degrees centigrade, or a boiler which cannot withstand more than 200 degrees, 200 bar pressure, or what will be the minimum safety factor, or which are all the approved materials to be used in this region of the world. Similarly, from the safety point of view, what are all the operating conditions, if those conditions are going to be getting altered, or we are going to exceed any of those conditions, then what are all the precautions to be taken? Are we going to give some additional stiffening? Are we going to give some additional ventilation? Then the environmental conditions, that means while manufacturing, how this part is required to be manufactured, what are the corrosion protection requirements to be done, how this part is required to be disposed, what can be used. There are certain materials which have a higher percentage of certain alloys which are harmful, so you cannot use them, you have to restrict them. So there are certain requirements which are going to flow like this, and then all this will get translated into design, inspection, testing, non-destructive testing methods and standards and codes. So welding engineer has to learn, understand each of these aspects, and then accordingly look for what will be the right process, what will be the right manufacturing sequence, and according to that, do we have infrastructure, machinery, and if we have, then what kind of a process and consumables we are going to select. And once the process, consumables, infrastructure, machinery is selected, and the above safety and environmental norms are being understood, then we decide on the PPs, personal protective equipments, which are to be used while operating this, or if we have to create a particular environment, a dust-free enclosure, humidity controlled enclosure, similar to that, we will be doing and analyzing it. Now we have done the basic requirements of it. Now we are going to translate this into the execution. The first step of execution is to train and qualify welding process. Once you get the requirements as per the welding process and the standard which you are following, let's say we are following section 9, then according to section 9 we will be classifying the materials in different P numbers, consumables in different F numbers, and then we will be writing down what parameters we are going to use. If we are going to have an impact property, then the supplementary essential variables are also going to get listed, like we will be writing down the speed, whether it is manual or automatic, and then we are going to then convert this into the non-essential variables, like how we are going to do the edge preparations, how we are going to do interpass cleaning, the placement of beads in layers and passes, then how are we going to dress up the welding, if there is going to be any repair, how are we going to gouge, which process we are going to use it for filling up that repaired portion after gouging. All that will get listed into our WPS, and accordingly additional welding procedures, if required, are qualified, and then we need to qualify the personnel depending upon the type of joint, depending upon the position in which we expect that particular joint or the number of joints in that equipment are going to come, the environment in which he is going to weld it, the machines on which he is going to operate. So welder and welding operators will get qualified. Then the role of a welding engineer changes. Now everything is set, job is already cut, rolled, machined, drilled, and setup has been done. Now he has to execute the welding. So his role is going to be like a supervisor, supervise the operations, that setups are coming in good condition, the cleanliness is maintained pre and post, and during welding controls are exercised, proper dress ups, and then offer it to NDT to ensure that the joints are defect free. If not, the non-conformance is required to be reported, and the repair activities as permissible by codes and standards is carried out. And then you document all these things, and if there are any non-conformances, not only in the welding but in distortion or in the dimensions, is required to be reported. If fixturing is required, that is analyzed in the stage 2 in the plant to meet the structural integrity, you normally design a fixture, or for a process you have a fixture. If there are two nozzles which are required to be exactly 1 meter away, then you have to tie these nozzles 1 meter away and fix it onto a pressure vessel, so you require a fixture. Or you want the tray support rings to be perfectly perpendicular, then accordingly you can have a fixture or a proper selection of a process like double operator technique, and then you choose different positions to ensure that structural integrity is also maintained. However, even after all this planning, in case there are non-conformances, then you choose to look into the root cause analysis, what we missed out in the earlier 4 bullet points, and try to develop that knowledge and document it for the organization, so that next time we have a similar vessel, this knowledge which we have documented, including its non-conformances, is helpful to prevent the possible non-conformances in future. Now that we have understood the role of a welding engineer, let us see if we can organize ourselves properly. And these are the steps. When I mean steps, either we can have a person dedicated for that activity, or a person having 2 or 3 responsibilities, but ensure that these activities are being done. So the first is having a welding engineer's presence at the design office. So when the design office is doing a detailed engineering of our part or of our equipment or sub-assembly or assembly, then at that stage, depending upon the accessibility, depending upon the requirements of the properties, ease of welding, ease of fabrication, ease of handling, the number of subsystems in which we will be executing the fabrication and then doing the final welding to have a full subassembly or equipment. All those discussions are done, the codes and standards are referred, understood. If there are any heat treatments required, if there are any special precautions which are required to be taken on the reinforcement, on the penetration, if these joints are going to become single-sided because of certain fabrication requirements. The next step is to have a welding engineer in planning, as explained earlier. Now, since we have got overall idea as to how the entire welding operations are going to be carried out, and proposed welding process. The joint designs have been already identified. Hopefully at this stage we also have got a clarity in the positions in which it will be welded. So accordingly we need to now start planning on the time frame. We need to start planning on the consumables, type, size, specifications, and which are the properties these consumables are supposed to meet, under what conditions we may have certain additional requirements getting superimposed due to our fabrication, like after 2 or 3 shells are welded, then we are going to have 2 sursims, and at that stage, or for a dish stand when we are going to have a long sim, before we form it, it may have a heat treatment requirement which is not specified by the customer, but that's a good engineering practice which we are incorporating to avoid locked up stresses before we take it for the subsequent operations. So like that we are going to really work upon in the planning and decide on finalize the consumable quantity, type, size, specifications, and superimposing requirements. Then of course there has to be a welding engineer who will be supervising the training qualifications as explained earlier, and the last is on the shop floor who will be executing, coordinating with NDT, coordinating with the various other shops to ensure that his output is the right input for the subsequent departments, and similarly ensure that when the assemblies are coming to him for welding or being done the setup, and he has to provide welders for tacking, whether the input conditions for him are the good conditions. That means the edge preparation is good, the angles are good, root face, root gap has been properly maintained, cleanliness has been done, NDT on edge preparation if required has been already done. So similarly the second team shall be into the design team, which will look into the core standards as explained. Planning has been explained. I think I have covered all of it in my first point itself, and this is the way, if really you see this particular chart here. Now let us come, what is the order of importance? I am sure that those who are going to look into this slide for the first time, they are going to jump on me and say that PP, environment requirements, safety requirements are coming the last in the order of importance. The assumption here is that the bare minimum requirements for safety, environment, PPs is already taken care. However, what is coming special from a given equipment which we are going to fabricate now, or a part or assembly, and depending upon its materials, metallurgy, how the environmental conditions, the PPs are going to vary or change, that you will have it only when you have the full understanding. So the first, I think 50 to 60% of this one is required to understand the metallurgy. Unless and until you understand metallurgy, you will not be able to decide on the processes, you will not be able to decide on what kind of structural integrity, dimensional control, distortion control, how difficult, how easy it is, what kind of a fixturing, purging requirements, trailing shield requirements, or the process requirements are going to flow down. So the choice of consumables, environment, if specific environment like discussed earlier, on humidity, on temperature, on dust particles, on overall cleanliness, even using hand gloves like a surgeon or the nurse uses. That means our sweat or any infection which we are going to carry with our hands shall also be not taken towards the weld joints, because that is all harmful for certain alloys. So then comes the NDT, depending upon the NDT, and then comes the fixturing, manipulators, positioners, rotators, the column and boom, or any other automation like Kobo, Robo, and then what kind of a weld edge preparation. This is all going to be discussed in this sequence. First understand the metallurgy, then understand the process and the structural requirements, then go to NDT and understand what kind of defects are acceptable or not acceptable, which are the methods which we are going to follow, and then work on fixturing and then work on PP. Only when all these activities are done, the welding engineer has really understood and done his job. So this is only the order of importance, the priorities. In case for a particular metallurgy having complex fixturing, like for aluminium, creating a complex fixture being a soft material becomes sometimes difficult. So you have to think, or fixturing itself is not possible. So go back and see, or the need for fixture comes in only when by proper sequencing, we are not able to control the distortion. Then only the fixturing has to really take place. And amount of fixturing also is required to be decided properly. You cannot do extensive fixturing by you have limited accessibility or limited movement, and then you have to do quite large number of start and end points. Like titanium, if you have large number of start and end points, it is not really good. The material is not that accommodative like carbon steel, where you can have as many start and end points, because the flowability, the surface tension, the weightability of this material, like carbon steel, to a certain extent stainless steel is good. But as you go into the higher alloying content, about 5% and above, and nickel, cobalt and titanium based alloys, then the flowability, the viscosity of the material becomes like a honey. It doesn't flow, it doesn't move, it doesn't penetrate by increasing current or voltage. So you have to have that much of gap to really penetrate, or you have to have movement of the torch to really move and spread the material on both sides and ensure that you have a proper fusion. So this way the order of importance has been decided, and we go based on this. Now there are few good to know points in welding. Every weld has shrinkage stress. We cannot avoid, because we are going up to melting point and then trying to solidify. In situ solidification in the weld edge preparation, and that too also it is not uniform all across. As we are progressing our weld, accordingly the weld is getting progressed and processed, so it takes certain time. Welding has three sides: weld composition, metallurgical properties of the basic weld. Now this being the as welded condition, we need to be really worrying about it. Plus there is the parent metal is going to melt, plus the consumable is going to melt. So the resulting chemistry after anticipated dilution from the parent metal and the burnout of the consumable, we will understand what is the metallurgy which we are likely to get. And if this metallurgy falls into one of the known materials, then the properties will be known. Otherwise we'll have to really do a testing, understand the behavior, the material characterization. So weld chemistry is very important to know. It is not the chemistry of the electrodes or the consumables, it is the chemistry of the resultant dilution which is going to come from the parent metal and the consumables what we are using, and the process in which we are using it. The second is the parent metal itself, which is undergoing different heat treatments kind of a thing, because of the different cross section from the weld towards away from the weld will undergo different thermal cycles. Some of the cycles will be hardening cycles, some of the cycles will be stress relieving cycles, some of the cycles will be half annealing cycles, some of the cycles will be normalizing cycles. So each of the cycles on that parent metal is going to be different. Weld, as we said, is a cast structure. It's a dendritic structure and behaves much differently than the rolled rod structures. So we must understand as welded properties of the alloy and the selected consumables. Uncontrolled welding, position, process parameters may give a uniform visual look, but will surely have different percentages of non-conformances, defects, or the locked up stresses. So once a WPS is written and accepted, a draft WPS has to be qualified by performing a test called as a PQR. And once a PQR is correlated to a WPS, we shall not change any parameters written in that WPS. That's the rule which we must follow for the critical equipments and even for the normal equipments if you want to have repeatability and consistency. When weld metal is into the molten stage, it has almost 10 to 100 times higher gas absorption capacity. That means if we are using argon, helium, CO2, mixed gases, or we are going to have flux which is burning either in the electrode or in a flux cord wire, or we are going to have a chamber in which we are going to do the welding. Each of these gas will have a solubility or the absorption into the weld metal, and this gas is, as I written here, 10 times higher absorption or the solubility. Now, unless and until we give sufficient time for weld to solidify, and while solidification ensure that these soluble gases or the gases which are absorbed into the weld metal, molten weld metal, are released, then only it will not reflect it into the porosity or some kind of inclusions, and such porosities or inclusions may be a trap for hydrogen to get collected, and once this hydrogen, which is the finest particle, gets accumulated there, the pressure keeps on rising in that cavity, and that leads to a very high stress concentration at microscopic level and creates a notch. And if you have highly stressed or highly hardened or high strength materials which has martensite or ferritic structure, this hydrogen becomes detrimental. And if there are service conditions which are going to have cyclicity at higher temperatures or at higher pressures or at higher loads, this entrapped hydrogen gas in this porosities or inclusions, which has already created a small notch because of its high pressure, starts propagating that notch into a crack, and a phenomena called as a cold cracking or delayed cracking takes place. So we have to be very, very careful in keeping all our gases as low as possible and have sufficient time for cooling so that these are driven away between solidus and liquidus so that we land up into no defect. The best way to control distortion, everybody knows, is to work along with the neutral axis, where either side of the neutral axis, use staggering, use locking directions for every joint, do balancing of the weld deposition on either side of the neutral axis or either side of the joint, choosing the right processes, choosing the right parameters, bare minimum heat input, heat extraction, a good weld edge preparation, control number of passes, layers, position them well so that you have sufficient gap for every pass and for every layer, and document all this, recommend all this into your WPS so that you follow it every time and we get consistent operations or the readings. Hope this second part of our video also you liked it, knowledgeable, and we will keep on doing this kind of videos on welding fabrication to have equipments which are far better than what is prescribed in the code standards, and that's how we will differentiate ourselves from the rest of the world or from the other fabricators and win this global competition. Thank you. Hello friends, today once again we are going to talk something on welding, and as you see here in this chart or in the slide, we will be talking about the type of joints and how we want to fill up these different joints, and to make that easy, how code has given us opportunity to classify based on the filler number, or as we discussed earlier, based on the resultant weld metal composition, which is nothing but a number, which we'll be seeing it in the next slide. So first let us understand what are all the different joints. As you see here on the slides, there are 4 types which I have classified. You can classify more and do detailing of these joints for ease of our understanding, and also the type of joints we use on our regular equipments, parts, assemblies. Those are required to be detailed out in much more as we go further. We'll see in the third and the fourth slide how it will be seen. So there are butt joints, the square butt joint, which is the simple, where there is no edge preparation. You just cut the plate right angles to the surface and bring it together with whatever the specification, that means either a zero gap or with some gap, and then with backup or without backup. So accordingly you make a joint. Then if the thicknesses are more, normally square butt is used up to 2 millimeters or 5 millimeters depending upon the process. For a TIG welding or for SMW welding, 2 millimeter to 3 millimeter is what something you can penetrate very well and achieve a good penetration on the other side of the weld. But if you have processes like plasma or activated TIG, concentrated TIG, or very high end processes like laser and EB welding, you can penetrate even square but much higher thicknesses, going from 5 millimeters to 10 millimeters. And if you have really a super high kilowatt rating of your EB welders, then you can go to 70-80 millimeter thickness also. But if that kind of a processes are not practically possible, expensive, or not available, we can switch over to a V joint, Z joint, U joint, single V, double V, or single J, double J, and then whether it is equal or unequal thickness which you are getting joined, or equal or unequal in the distribution of the groove on either side of the weld. What is the included angle? We normally recommend 60 degree, that is 30 degree on each plate, but there are joints which will be saying it where on one side there is no possibility of giving a edge preparation, so the entire angle is adjusted for accessibility on one side of the plate, and accordingly the weld edge is prepared on one side or both sides, equal or unequal. And the most important is that after we select the type of joint, then we decide the micro details of this, like root face, root gap, for getting different levels of penetration. And if there are partial penetrations, we can compromise on these root gap, root face, included angle, and other details. Similarly, we can talk of the fillet joint, single sided, double sided, single run, multi run, equal, unequal length, on similar material, dissimilar materials, what is our electrode war or the process what we are using, the positions in which the butt joints and the fillet joints are being done. The third level of the joint is the overlay or the cladding or the buttering, where on a piece of plate we will be depositing different layers, different passes, and then we will be achieving either corrosion resistance, or we will be achieving hard facing, very hard surfaces, or there are sometimes some directional strengths are required, especially in the Z direction, to avoid lamellar tearing. We do buttering. or there are sometimes reclamation built up is required on a worn out part or a wrongly cut part to restore the geometrical tolerances. So buttering is employed, and then we also have a spot weld or a tack weld or a plug weld, or there are tube to tube sheet weld. So there are many types of joints which we can classify and use it. So we must list out for our job or for our type of product or the normally preferred joints or normally used joints in our manufacturing areas, and classify them to the extent possible, make a table, recommend for different materials, for different processes, for different thicknesses, for different positions, all the variables a welder is going to be concerned about, and also on depending upon the filler metal, parent metal, and the resultant chemistry. So to get a feel of the consumables and the resultant chemistry, let's go to the next slide. Based on this joint types and the selection of the consumables, we will be deciding the number of passes and how to lay them and what care is required to be taken. So let's move to the next slide now. In this slide you see that we will be talking about the F number. Typically the F number is the classification of alloys, as you see here. One is for carbon steel, carbon manganese steel. If you go to let's say 7, it is the chrome steel 400 series, that is ferritic martensitic series. If you go to 11, it is the high strength low alloy steels. Or if you go to 21, it is for the aluminium. If you go to 40 series, then it is for nickel based alloys. If you go to 50 series, it is for titanium. 60 series is for the zirconium. So like that, different series and different 1, 2, 3, 4 numbers or ABCD classifications, as many types based on their melting characteristics, melting temperature, the various effects which are listed here on the viscosity, on surface tension, on the inclusions, on the solidification pattern of this, we classify into the F numbers. And as you see here, we have a P numbers which we use it for the parent metal, F number for the welding consumables, but the A numbers are used for the resultant alloy. That means this solid line here and the dotted line, which is the initial edge preparation, this is the distance or this is the thickness, the penetration is going to melt the parent metal which has a particular chemistry. The F number comes from the consumable which has another chemistry or maybe a same chemistry, and depending upon the dilution. So for example, let's say that both ends we have a dilution factor of 10%. That means the resultant weld metal is going to be 80% of the filler wire or the ferrite metal or the electrode composition, and 20% of the resultant weld metal or the A number is going to be from the parent metal composition. So for ease of understanding, let's say we have a carbon percentage of 0.1 in our parent metal or rather in the filler wire, and 0.2 into the parent metal. So now we are going to have 10% on each side in the resultant metal. So 0.2 of the parent metal, 20% of that, that means it is going to be 0.04 what is going to come from the parent metal, and 80% of 0.1, so that is 0.8. So that means 0.8 plus 0.04. So we are going to have 0.84 as our 0.084 as the composition of our, I'm making a mistake. I think let's do it again. What I said is 0.2% carbon and 0.1% carbon. So when 0.2% is going to be on the parent metal and 20% of the weld metal is going to be coming from parent metal of 0.2. So 0.2 into 20%. So that brings us 0.04, and the electrode is going to be 0.1, so 80% of that, so it is going to be 0.8, and 0.8 plus 0.4, so it is 1.12. uh, 0.08 and 0.04 add will to 0.12, so it is little more than the filler wire, and that's how the A number differs from the filler wire or from the parent metal. And therefore the three numbers are very important for us: the P number, F number and A number. Now once we understand that this is going to be a different, we also see that the fluidity of the molten metal, which is also a factor for A numbers to separate it out, or there are certain alloys which are sluggish, and they are sluggish because of the diffusion kinetics, how the parent metal and the weld metal are going to really adhere to each other, and that depends upon the sluggishness or the viscosity or the fluidity of the metal. The surface tension of the material improves and the material flows if the viscosity is low, fluidity is high, and the kinetics or the dynamics of the liquid alloy or the fusion kinetics is surely going to improve upon it and has a better fusion. Now, looking at the earlier slide of the various types and understanding of this filler metal, let's go to the next slide where we'll be talking about positioning of layers and passes. The positioning of layers and passes is, as you see here in the first center, this one, that we have a hot pass, the root run as we call, and then we have the fill passes, and after the number of fill passes we have the capping or the covering layer. So that is also described here, and as we see on the visual, the internally, if you see this, you see clearly two lines. One is the fusion line, another one is the penetration line. Like in earlier slide we saw that there is a dilution which is coming. So similarly a dilution happens between the layers and between the passes also. So every pass may have a different chemistry, every layer may have a different chemistry based on how much dilution we are permitting. If the dilution is going to be less than 10%, it will not create much of an impact, but if the dilution levels are higher, then it will have an impact on every layer, and that is where we need to ensure that we position these layers very well from the metallurgical point of view and also from the non-destructive testing point of view, because based on this positioning of these layers we will be having what is the resultant gap, and that we will be seeing it in our next slide. But see here the type of joints. For a butt joint we have 1, 2, 3, 4, 5, 6, 7 layers have been done here. Now if you are depositing 1 and 2, your original edge preparation you started with is almost intact. However, the profile of this first shall not be very concave or convex, should be as flat as possible, so that the layer 2 can be deposited very well without having any imperfections at these corners. If it is too convex, then this the edge preparation is going to be really difficult, and that is where we are going to go back and really see how we are going to deposit these runs so that the fusion on both ends is going to be good, and also we will be having a good amount of fillet joints for the getting the throat and the leg lengths. So normally in our WPS we just write down this number of layers. What I want is really if you can make for the number of passes and the layers, if we can specify what are the current voltage we are able to give, and also if we can give what should be the minimum gap between each layer and a pass. If we are able to do that, like here we have given example that for a 1.2 dia wire, if we can keep 2 to 2.5 millimeter gap and a proper angle, then like we maintain root gap, root face, weld edge preparation for every layer, it shall be for every pass also, and that will give a sound weld which will have a good fusion, which will have a good metallurgical characteristics. The dilution levels can be also maintained. The heat input, as you see here, is varying in different this one, especially in the single V joints. It is becomes very difficult because one side is almost square, it's square, and the other side is having an angle, and you have to have accessibility to ensure that this vertical edge is also fusing, whereas the inclined edge is also fusing, and between the layers, that is between two. Hi friends, once again in continuation with our efforts to understand welding better, a different kind of a welding application which we use it, which you can see on your screen, is buttering or overlay or hard facing or reclamation or built up. That means we are going to use the welding process or processes to deposit material such that it will give some unique properties, or it will help in building up the lost thickness, wear out thickness, or for any other physical or metallurgical means. So what are those overlays or the buttering? It is typically being done either on the edges or on the surface, but when it comes to putting it for a corrosion resistance, the internal surface of that entire reactor where the corrosive chemicals are going to get reacted, I think that gets onto every portion of the internal part of the. So that means we are going to have it on the ID of the nozzles and the entire shell, dish stand, and any other surface which is going to come in contact with the corrosive liquid. So that's the way we will be looking at it. And this is, as I said, for building up a thickness which is good to take care of the service life. It may be 1.6 millimeter, 3 millimeter, 5 millimeter, depending upon the service and how aggressive is our corrosion. Sometimes it is used for hardness, that is for hard facing. So you want, like in earth moving equipments, you want a very hard surface which is going to dig into the mud or soil, or going to lift heavy stones, or it can be a part of a crusher, or it can be a part of a shaft where you are going to have the bearing surfaces. So all such areas you require a very high hardness, crossing sometimes even 60 HRC also. Or there could be any specific property you are looking for. Maybe on a hard surface you are looking for a soft surface, or you are looking for creep resistance in this. So it all depends upon the application. You have to choose the consumables. And the third application is like a lamellar tear, as you see here in this particular sketch. This layer which is given here is to prevent the lamellar tear, which is happens because when you have very thick rolled plates in the Z direction, the sufficient grain orientation doesn't get, the compaction of the grains doesn't happen in the Z direction, and that's where we get a lower strength. So you dig away or take away some material from the parent metal which has Z directional low properties and deposit weld metal like shown here. So it is called as a buttering or a layer to prevent the Z direction. It's kind of a built up, but that's deliberately you remove material and built it up so that the weld is able to take in the Z direction the stresses which are going to come after you weld this vertical member or a beam. And when we are welding and doing buttering, that time there is no stress because it's kind of a bid-on plate, so you don't land up into it. Now what we are going to see in the next slides is, like any other welding, what are all the care and precautions we need to take while depositing either the complete buttering on one side or on one of the plates, which is maybe a mild steel plate, and the other side is stainless steel, and you want to join it, so you butter it with 309 stainless steel grade and then weld it together with 308. So either you can do that, or you have buttering or hard facing, so you deposit layers and passes to match up as shown here. So this is how we have to really look into it. So let's go and see the details of welding now. Okay, so a normal weld bead which we deposit looks like this. So what are all the important parameters which we do it for butt welding also, but they become little more important when we are going to do a overlay, where we are going to do side by side lot of layers, and even a fine porosity, crack or inclusion in the surface of this weld will get attacked with the corrosive liquid. So the two important parameters here is the overall thickness of the weld deposited, as the one which you see it on top of the plate, and there is something which is below the plate, and even beyond that there is a heat affected zone, as we get in any our other welding. So you have basic welding deposition here, that is the primary surface, but there is a diluted layer, and beyond diluted layer, depending upon the temperature the parent metal or the base metal is going to see, you are going to get different structures, and some of them are hard. So those are the ones which are really worrisome for our heat affected zone, and others can have slightly stress relieving, so a lower in strength also sometimes you get. And this is a beautiful picture which gives how the dendrites and the solidification is going to happen with the number of passes, and each pass, so you observe here that we have the penetration side, the heat affected zone, but important is that you see here even the angle is also mentioned. So we should have very narrow depth of penetration as seen here, this particular one, and as wide as possible. It should not be sharp. In our next slide I will show you how a typical butt joint weld penetration, if you cross section, it will look like. So we try to give as flat as possible, as low in the depth, and that's the technique which is different from the normal butt joint or a fillet joint, and that's where there are special slides which have been prepared here. So the configuration of this profile, the weld profile, is very important, and that is where this angle comes into a play, because our second run is going to, the pass is going to be either on this side or on this side, which we will see it in the next slide, and that must get properly fused with this entire line here, as you can see here the overlap which has been given here. And the weld bead with the penetration pattern, if it is so deep, then the dilutions are going to be very high, because this is what is going to be the diluted material, and we want the bare minimum dilution from the parent metal to come. So we may use little higher arc length for overlay, which we don't use it in our butt joints, because there we are concentrating more on penetration. Here our focus is a very shallow penetration, wide bead, and a beautiful angle. I mean, the angle as it is shown here should not exceed 60 degrees. I mean, ideally it should be between 45 to 60. Very smooth profile it should have, but if it goes beyond 60, it becomes too sharp for the subsequent run to get properly deposited. As you see here in this slide now, the number of layers, the overlap has been shown as a half of the base metal overlap, which in turn comes to about 30% on this where it goes, and then the rest everything is going to see it. But another important parameter which I want to show here is, see this red and yellow portions, they are our penetration side, and the penetration should be as uniform as possible as shown here. Still there are few areas like this P here which is larger, here it is lesser, and this is something which will give us trouble in our bend test. So a very uniform, as you see on the top of the surface, we should be able to see it at the bottom of the surface also, and not creating any anchoring which can lead to failure in our bend test. So the top also shall be as uniform as possible, as flat as possible, so that the subsequent layers we can once again deposit with 10 to 12%, 15% penetration. But if this kind of anchoring is going to happen in the subsequent layers also on top of this, then the dilution levels will be higher, and a clean chemistry which is required for corrosion resistance or for hardness, you may have to deposit one extra layer which is going to be expensive. So we have to take care in the first layer itself, like a root run, that we don't give much of a dilution but have a very good bond strength of that is required to be really achieved, and at the same time we don't miss out on our other parameters. There are variations in the slide which is shown here, and that is something which is not acceptable. A large variation should be as uniform as possible. Now these are the typical weld geometries what we are seeing it now. So if that angle is not maintained, as I said, then you will have something like this, very sharp. See, these are all which are not acceptable. Only the smooth ones which are having a good contour will be good, and if we get that, then your barrier layer, the first layer and the second layer will also have a very good uniformity. Finally, the joint should look like this. That means you are going to have first a butt joint below it with number of layers and passes, narrow or regular, conventional, and on top of it, to have a good corrosion resistance, you are going to build it up, this additional material on top of the weld. So unless this weld is sound, your overlay will not be sound, and positioning layers and passes in this buttering or overlay also becomes very, very critical and important for us to really do it. So that's the importance which we give for the overlay. See how beautifully they have done it here on the OD. On the ID also we can achieve a similar kind of a thing. Given small diameter tubes, there are mechanisms which are developed where we are able to do with the TIG welding, and 1.2 millimeter wire deposition on the internal pipe for developing a nozzle or for a passage of corrosive liquid on top of from inside it, and that's the way we'll have to really worry about it and look into it. So I hope that you are enjoying this type of welding also, and understanding the features which are required to be done. So I will repeat again that the angle, the depth, now this kind of a penetration is not acceptable in overlay. We must get the flat as I showed you in the earlier slide. Width should be as maximum we can get it using diameter into maximum 2 times, or if it is make submerged arc, depending upon the voltage arc length we are choosing, it can come to that extent. And this is the way we should start developing our welding techniques. So thank you for listening to this video on overlay, buttering, hard facing, and different entities which are required to be done and achieved. So what we actually get is a dye penetration test to see that there are no surface defects allowed, because any surface defect means crevice corrosion is going to increase. Hard facing will have a crack initiating from there. Built up, if it is there, it is not going to be a sound metal for us to have a built up. If it is for lamellar tear, then that could be a potential point acting as a notch. So a lot of care is required when we are going to do this build up. We can also do ultrasound to see the bond fusion, because DP will give you only the surface defects. Ultrasound will give you if there is a good bonding, if there are any side wall fusion issues, if there is any penetration issues in number of layers which we are going to do it. So every layer has to be thoroughly cleaned. If you have any doubt, grind it to white. Don't see any undercuts, and then do a DP, and then once the DP is properly cleared, washed, then you can deposit weld material on top of it. So not only welding, while taking NDT also you have to be very, very careful. Post NDT, clean it before you start the subsequent layers. The cleaning has to be as thorough as possible, and wherever you have doubt, grind it, so that only wire brushing or acetone cleaning should not be trusted and believed. Thank you so much. Hello friends. We are going to discuss today about one more type of welding. As you see here in this chart or the slide, it's a fillet weld. As the description given here, you see the fillet weld joints are not only the most frequently used weld joints, but also one of the most difficult to weld with any real degree of consistency. So we are going to discuss as a primary observation, fillet looks to be simple to weld as you see the entire fillet welding yourself, unlike the butt joint where we are going to hide most of our runs in the subsequent layers and there is no visibility as to what is happening inside the groove. But any type of a fillet joint, as you see here, whether it is a corner joint, single side, double side, or we have these are kind of a lap joints, these are corner joints, but this is a classical fillet which is shown here with its root, throat, which is explained better here in this real photograph of the fillet, that you have a vertical member and horizontal member put at normally at right angles, but sometimes it may be at some included angles in case of a structural welding like TKY joints, where there would be a small angle going from 30 degrees to 45 degrees, and the fillet is after the butt joint. But most important part, what we need to understand, unlike a butt joint which has a full penetration, fillet through this vertical face of this vertical member, the horizontal face of the vertical member, we are not going to fuse it all through unless we give a groove and a fillet. So groove and fillet joints are also used quite often where this kind of a stress risers or a notch is not acceptable, and critical equipments like in nuclear and other industries will have many times even this vertical member which has a slight groove or a Z both sides or single side, and then it is welded first and then on top of it we build the fillet. But if we consider only fillet weld, which is most of the times we use it in our pressure vessels, we have to look into two important parameters. The fillet design, unlike in the butt joint where we very rarely weld partial butt joint. Always whatever is the thickness, that's completely filled up with proper root penetration and reinforcement on the top. But in case of fillet, depending upon the stresses which are going to come, which we'll see in the subsequent slides, we will choose the throat. Even though the leg of the fillet is easy to measure, this is the leg of the fillet, as you see here, the L and L. But what is important, where the actual load factor of the fillet is going to be taken, is this, the cross section of this weld. So this is called as a throat, the theoretical throat and the actual effective throat, because of the penetration or reinforcement or concavity. The resultant of that will give the actual throat, and that's what is going to carry the load and the stresses between this vertical member and the horizontal member. So what we are going to do is we are going to see how to deposit this weld in a proper manner, and how do we ensure that we achieve this throat and at the same time there are no defects. So like any other our weld principle, if you cut right, you set right, if you set right, you weld right. That applies even the fillet also, that if we are able to really put this vertical member on horizontal member with as close gap as possible, that means this edge preparation has to be cut correctly. This plate shall be as flat as possible, the horizontal plate, and we should try to fix it with the 90 degrees on both sides, that is right angle, and tack it and ensure that it doesn't bend. Otherwise we'll see in the subsequent slides that how, if the plate gets inclined, or for lap kind of a joint, if this plate which is on the top gets lifted up by some distance either at the joint or at the other side, it is going to create a improper joint there, and then welder will find it difficult to weld. Now why we are saying this is a little difficult to weld as compared to a butt joint is, in a butt joint both sides are normally kept same, unless it is a single V and we have only one side, then it becomes difficult to weld. But in fillet, even though we have full accessibility, the placement of weld bead to achieve correctly legs and the fillet or the throat is the most important criteria, and this placement has to be done in two directions, which we are going to see it in the next slide. So I will move to the next slide now. Now as we were discussing, say one of the angle where in the direction in which we are welding this, so that angle of the electrode is required to be maintained as suggested here, 60 to 70 degrees. For most of the processes we maintain this 60 to 70 degrees in the direction from where we are going to continue. But in the other direction, the cross section of it, we have to be as perfect as possible depending upon the position where we are putting it the fillet. So as you see here, for the first layer we are starting with 45 degrees, but as we go to the second layer we don't want it to spread onto the horizontal plate, it should be on more on to the earlier fillet, so we increase this angle from 45 degrees to 70 degrees. And similarly, if we are going for the next one, I know that this video we are getting our thing, but I will try to move it when the move will be made. And here if you see, this angle is exactly reverse. We go from 45 degrees to 30 degrees so that we place maximum welding on the vertical plate, and by gravity it is going to fall down. Here by gravity it is going to fall down, we are deliberately putting it onto the earlier fillet, so angle is 70 degrees. So this maneuvering of the torch angle, weld angle, or even our submerged arc welding when we are going to place our torch or the nozzle, and on the other direction it has to be 60 to 70 degrees. So this is one difficulty what we face, and as you see here in different passes it has to be maintained. The fillet may not be achieved in one single run. There are few methods which is not very widely used, where in single run we try to cover by little weaving, which I will show it in the next slide, for nozzles. But most of the time we will build it by placing number of runs. So first we'll create a fillet, suppose the fillet is of 20, first we'll create a fillet of 8, then 12, then 16, and then 20. So the number of runs which are going to increase from 8 to 12 to 16 and 20 are quite large, quite big in number. Here it is only one fillet which you are seeing it. As you see here in this photograph, see the number of fillets how they have done it, and so nicely they have done. So what is important for us, which we'll be saying it in our third slide, is where the the concentration, the stress concentration is going to happen, and where after welding there will be a internal stress which is going to get developed because of the shrinkage. Like a butt joint, there is a shrinkage. Here also there is a shrinkage, and it is said that if you take two plates right angle to each other and try to put a tag there, the amount of force by one single tack of 3 millimeter length by 3 millimeter fillet can take few hundreds of tons of load, or can create a shrinkage force. And that's where a very thick plate also you will see, starting from the fillet, it bends. It either goes this way or this way depending upon where you are going to do a fillet. And that's because, once again, like in the butt joint, here we have the least of the weld, and here we have the very large width of the weld which is going to shrink. So the shrinkage here is less, shrinkage here is more, and natural tendency for this, the vertical member, is to bend down towards the horizontal member because of this larger width of the weld which is going to shrink. Now, to avoid that, we have to ensure that nowhere in the corners we will have a stop and end point. As it is, the corner joints are already highly stressed, and the last weld which will be doing it here, which you will see it in the subsequent slide, is also a highly stressed one, because already there is so much of weld which has happened before we deposit the last layer here, and we will start building up from the bottom. So the last layer is always going to be from top to bottom. Now, while doing that, like in the butt joint, we also have to check and ensure the setup. So a good setup can give a possibility of very good weld. A bad setup can create a problem for us. We will not be able to measure the throat correctly, we will not be able to weld it correctly, there will be a air gap which is going to be remaining here. And if it is a fillet with a lap kind of a joint, there is a possibility of the corner, because of the arc voltage, getting melted down. And if we are not going to give the fillet, we have to be very, very careful in directing, and we may go from 45 degrees to 70 degrees to avoid this corner joint or corner melting. Otherwise it will be a defect. And if we do too much of vertical 70 degrees, there is a chance that we may have a lack of fusion on the horizontal plate or the second plate, and that may create a problem in the weld. It will be a defect. So while welding a fillet, so many areas, so many angles are required, unlike in butt joint where we have only one direction to really monitor and see that we have sufficient gap for depositing. Here there is no question of gap, because everything is open. We have to ensure that what we deposit is the right way, and if we make a mistake, not only the fillet leg or the throat will not achieve, but there could be a excess deposition on one side to achieve the throat, or there could be a concavity, or there is a convexity. Both are not good. If it is too concave like in this photograph, or too convex like in this photograph, the toes or the throat is going to suffer. The toes are very susceptible for high stress in this kind of a convex joints. And in concave joints, even though we measure the leg lengths to the requirements, but the fillet is going to be lesser to the extent of this depth of depression. So lot of things welder has to really do it and position it, and that's where I decided to make this 3 separate slides on the fillet, irrespective of the material. If the material is sluggish, and if the material is not going to flow, and if there are nozzles where the accessibility is an issue, then still further our welding is going to become a challenge. And that's where, don't take fillet welds very easy. They are also equally important for us. And a small defect or improper welding can create a failure. As we will see in the next slide, the stress concentrations are going to be much higher. Now we are on the last slide of the fillet. As you see, there are 2 types of nozzles, a set in nozzle or set on nozzle, and both have a groove to be filled up and fillet to be given on top of it. So a typical nozzle, welded nozzle, will look like this. There is a flange which is normally set up to the pipe before we put it onto the shell, and similarly if there is any secondary nozzle, that also is welded before we keep it, and both this flange and this secondary nozzle is the one which is going to create a hindrance accessibility for the welder. And then the shell radius, as you see here in this photograph, in the one side, this side of the weld, you will see a good joint which is coming up here, but on the other side this angle is going to become quite large, this angle is going to become less, this angle is going to become quite large. Similarly in this our the TKY joints which I gave example earlier in the structural welding, where it is not at right angles but it can be between 30 to 45 degrees or even 60 degrees, and then the accessibility in this corner here is very difficult, whereas almost out of 360 degrees, 20 to 30 degrees is only the most critical portion in this joint, which is very carefully required to be welded, whether it is a butt or a fillet. But on the other side it becomes much easy, but this is the joint which is required to be taken care. As you see here, the number of passes which you are going to do it and the placement of each of these pass becomes very critical. So coming back to our nozzle welder, what we do is the number of the weld lines or the number of passes in this area may be lower than the number of passes which are required to be built here, because our fillet is going to be measured from this height, as you see here, where we have to get the throat here, whereas here achieving a throat in this direction of the weld is easy, in this direction it becomes little difficult. So number of passes are going to vary. So how to start and stop this number of passes and where to merge as you take 360 rotation on the weld becomes important. And finally the stress values, if you see here in this particular thing, see what is the measurement near to the toe of this upper fillet, which is the last one to be welded, has gone up almost 33% higher, 30 to 33% higher, from 3000 water units to 4000. So there is a jump of almost 1000 units in the stress level, and that's how it comes into raid. So this is a portion, and both sides we are going to weld it, so it is not only this side of the weld is highly stressed, the other side of this plate is also highly stressed because there is a fillet on the other side. And if there are any defects which will land up into this because of the gravity, weld is going to fall down, and there are undercuts or there are improper fusions, the reinforcements are not good, then we will have the worsening of this already high stress level with the bad impact of the weld profile. So I will say that even though fillet looks to be easy for qualification in PQR or WPQ, but executing it onto the actual job with this reinforcement pads or without reinforcement pads is difficult. And that's where, to avoid that, sometimes this kind of a weaving with a very large nozzle to shield it is practiced, but more or less this is not acceptable by many codes because of the so much of weaving which is being done. And after weaving also, you are not sure whether you are going to get the sufficient the reinforcement on the fillet, otherwise there will be a recess as we saw it in the earlier slide, and that may not qualify for the required throat length. So positioning of these weld beads, getting this throat, ensuring that there are no defects, undercuts, no stress points, fusion between the layers, fusion with vertical wall, fusion with horizontal wall, all are required to be seen, taken care. And if it is a nozzle, and especially a nozzle which is at angle, it becomes still more difficult, and lot of practice, care has to be taken. I am sure with these inputs you will be able to really look the fillets into a different way, which is normally considered as very easy, is no more easy. Placement of fillets is very critical. The start of fillet is also very critical. Where are you actually tacking it so that you have the best point where it gets locked? Like in our earlier slide, if you are tacking it on the sides, if it is possible to do it, most of the time it is not there. So are we going to tack it on both sides. Alternatively, are we going to give some gussets to hold the plate in vertical direction, not allow when we are going to weld, we are going to check every time in case we see that it is bending towards one side. Immediately we should stop on this side where we are welding and go on to the other side and start welding from that side, and make it within the welding stresses itself. You try to manage to keep it vertical, or best is to really have both the welders simultaneously welding from each side, so that the stress levels are balanced and the job doesn't distort, or the vertical member doesn't bend from 90 degrees to either this side or that side. And then physically we will have to correct it. If you try to correct that physically without the welding, this highly stressed point which is seen here, the red line on the top of the fillet, is the one which is likely to crack. That is where the crack will initiate, and the weld will remain intact, but the parent metal will crack, and then we'll start blaming parent metal, or there may be an inherent defect. My welding is good. That may be a possibility. I'm not saying that the parent metal may not be bad, but since we know that there is going to be a stress concentration and the placement and the distortion, it is welder's duty to really see that while he is welding, it doesn't distort, it doesn't give more stresses onto the top of this weld. So this weld, the last weld, is the most critical weld which has to be deposited as shown here, and we have to take utmost care in this last run so that we don't land up into any defect, porosity, cracks, or the undercuts or linear indications in any of our DP or X-ray. Ultrasound and X-ray in fillet is not easy like a butt joint. Very carefully we have to do this test. A qualified person who has experience can only interpret it very well. Otherwise, as we saw in the earlier case, the root gap which is seen here, that may reflect as an indication for the fillet defect. So calculating where exactly are we going to this unfused area, which is not possible to fuse unless we give a butt joint here, like in this nozzle sort we do it. Normal fillets we just keep it on top of it and weld only edge to edge and not penetrate into the thickness side. So these are all the considerations which are required to be brought in, and once we do that, I think our fillets will be good. Lot of care is required to be taken in structures, in our pressure vessels, and especially when the equipments are for the critical applications. So that's why these 3 slides, in my opinion, are the most important for any welding engineer to concentrate. Enjoy welding, do it good, do it well. All the best. Thank you. Hi, good to get connected again on the topic of welding. As you see here, we have discussed many other aspects of welding and some aspects of the defects in welding, but today we are going to deal little more into the defects and what could be our approach to first detect these defects, and then how to overcome these defects in the easy steps. The left hand top photograph is the type of defects which we normally discuss, so I am not going to dwell more upon that. However, we will touch upon it. There are mainly 3 types of defects which we see it. The defects which originate because of the setup. If the setups are not done to its perfection, we have seen that root gap, root face, included angle, mismatch, and so many other possibilities by which you can see there could be a defect because of the imperfection in the setup. And these defects, or the remedial action is probably we know it, either we break the setup and try to correct it, but if that is not possible, then if we have anticipated earlier, we can give some taper to minimize the mismatch, or we try to do some wedging and we try to do excessive fixturing so that whatever mismatch or other setup defects, they will not aggravate it further, as there will be a welding shrinkage or welding distortions. But there is a limit, and finally we need to accept it, or we need to correct it post welding by once again either depositing extra layers so that there is a smooth transition between one end of, or the one side of the weld to the other side. And these are finally not a very good practice, and designers will have always a suspicion on how these products will perform, because they have taken care while designing that the mismatch and other setup defects will be to the minimum or zero. So that's the first one. The second defects is where we can see it by the naked eyes. Like the first one, the underfilled, we can see that welding has not been done fully into the groove if that is required to be filled up. Obvious, this one remedy is that we need to add more runs and ensure that the weld groove or the fillet or the overlay or buttering or the other applications of welding which are used are completely done to what is required as per the standard code or the design. The second defect is undercut, which is also a surface defect, and this welder will find it, only experienced welder will find it while he is welding it through his screen, but otherwise for a new welder he may miss out, especially the small fine undercuts which emerge on cooling. After cooling in the heated condition, you feel as if you have done a good weld, but when it cools down you see that there is a undercut, sharp undercut sometimes, which can be a stress riser. So if you happen to see these undercuts after the welding, you need to immediately little bit clean, grind, make extra space for you to weld, and deposit additional runs to cover it up properly. Same is the third one, the pore penetration. Like the underfill on the top side of the welding, there could be a pore penetration on the bottom of the weld, the other side of the weld. But for this you need to have access towards the other side and see it with your naked eyes. If you don't have access, like in tubes, pipes, or some of the big shells where you cannot go inside, then the penetration welder through his screen is able to judge that whether the keyhole what he creates while welding the root run, is that getting fully filled or penetrated. Indirectly we can see it based on the depth of the welding and the amount of filler wire he has consumed, and that could be another good indicator whether we have achieved a full penetration. Or else for these inaccessible things you may have to use a boroscope or some mirrors, or you may have to take x-ray, ultrasound, then only you will be able to see this pore penetration. The fourth defect, or the right hand top lack of fusion, is a defect where sometimes it is difficult to miss out with the naked eyes, because you see as if it is penetrated fully, so you assume that while it has penetrated, it has also fused on the side walls or the edge preparation which has been done onto the two plates or the two jobs which are getting joined. But actually it has penetrated, it has only come out of the groove, but it has not fused on the sides. Now surely if that happens, visually it is difficult to see it. The dye penetration test sometimes will reveal in case the root is penetrated and not everywhere it has fused. So visually you will not be able to see that, but the red dye will surely come out as you put the developer on the other side. The fifth one, the spatter. Obviously these are on the surface, visually you can see it. While welding also, through the screen you can see the sparks which are getting generated and the droplets of weld getting deposited onto the side of the weld on our jobs which are getting welded. and then this also becomes activity to clean. These could be sometimes big ones which may have a good fusion, so you have to grind and remove it, and these are not good aesthetically as well as in sensitive alloys like alloy steels. These could be a stress risers in case they happen to be the big ones. Porosity most of the time is internal, very rarely, or sometimes you can see it on the surface also open to naked eye and you can correct it. But surely an experienced welder can see the gas which is bubbling into the weld pool, and if it is having a very aggressive action there, then porosity is surely going to come. And good welders I have seen, they are able to get them improved while they are welding only. Either they will stop immediately, do whatever correction required either in the gas or in the shielding or in the angle of your torch or electrode or your other cleanliness issues if they are there for the porosity, and they will surely able to improvise it. But otherwise you will have to wait for X-ray to happen or a dipenetrant for a fine porosity which is exposed to the surface. The next two defects overlap once again by measuring the width of the groove and then later on finding it out what is the width of your weld, and then by using some very fine wires you can try to insert between the overlap region of the weld and the base metal, whether this overlap is it good or is it only on the surface. That means the excessive current has melted material more in the last layer because you are in a hurry to finish and go. So, but it has not actually burnt the parent metal which is required. The parent metal has to also melt to have proper bond or a fusion. If that doesn't happen, overlap is not good. Otherwise, having 1.2 millimeter overlap on each side is a desired welding practice, and one should have it. Inclusions, slag inclusions or other foreign particle inclusions, those are once again stress risers. It is a imperfection in the weld. It is not the weld metal which is actually conducting or having uniformity in the weld metal, and that's where it is called as a defect, and those are not acceptable. Those are required to be removed. Sometimes they are very brittle, sometimes if it is a slag it will be having no strength, and the cross-sectional area of the weld will substantially come down because of these inclusions, and you will not get the strength which is desired. The next defect, the last row, excess reinforcement. Now, any reinforcement which is a smooth transition, like a good speed breaker, if we are able to go over it, you hardly feel any jerk or a jump. But if the speed breaker is very tall, very narrow, very sharp, you will see whatever speed, even if you are going to go at a very less speed of 1-2 kilometers per hour, still you will feel a jerk. Even if your car is the high-end car like Mercedes, Toyota and all, it will still have it because the nature of the speed breaker, and exactly that's what happens. And you can see from the figure itself, and this is what the reality also many times we see. The welders who are not able to see the profile of the weld through their screen, they'll end up into, or the parameters are bad and they're using excessive arc length. This is what will happen. It will spread, it will have only in the center portion lot of deposition, but the rest of the area is getting melted and flown, and that's where the width goes up. So reduce your arc length, reduce your arc voltage, use proper current. I'm not saying that use low current or a medium current. Even if it is within the range, you should be able to do it. Or if you want really a wider width, you should weave it and have a dwell. The dwelling in weaving is very essential. Dwelling is you wait, stop at both the ends of the width which you are covering, and then allow that dwell, that is the wait period, to deposit more material there and improve the profile. Smooth transition is not a stress riser and it is good. Code recommends 1:3 taper for any smooth transition in dissimilar thicknesses, or wherever you have transitions in the nozzle or in our other areas in the pipelines or in the structural members. Cracks, obviously, because of improper shrinkage, improper parameters, improper welding consumables, you will land up into the metallurgical defects. The cracks, when the material is cooling down, it doesn't cool uniformly, and there are certain voids which create like a porosity, but porosity is a small defect, whereas here it is a large defect which actually creates a planar defect. It is not a volume defect, it is a planar defect, a crack, and those are very difficult to take up under the load. Cross-sectional area in that particular plane drastically reduces, and the weld cracks or the entire equipment has a failure. The last defect, that is the burn through, is mainly because of the defect which occurs when you use excessive current, larger gap, lower thicknesses, and improper welding speeds. So there are many reasons for burn through, and if you are not having a good control over your welding, the burn throughs are unavoidable, and once you have a burn through, you really make a larger root gap in that area, and then to fill it up is a real trick. So you should not try to bridge this gap, the burn through gap, in one go. Rather use a buttering technique after, of course, grinding and re-preparing your edges to smooth transition. Bring slowly material by depositing on both the edges to a desirable root gap, and then use proper current to fuse it again and join them together. If you try to join them together in a larger gap after a burn through, the weld metal will be very thin, and that thin material, while it is shrinking or while it is cooling down, the shrinkage cracks, it will not be able to sustain and it will crack. And this is what happens if you happen to make a concave welding in a root run. If you try to give a concave welding, then the thickness at the center of the weld becomes very less. It cannot sustain and it fails or breaks and looks like a burn through or a crack in the root run or in the penetration. And these are all the defects which only by improving parameters and adjusting your angle of the torch or of the electrode you can improvise it. So these are the standard defects which we have seen, but as we have been discussing, that welder's job is not only to make a good sound weld, he has to also ensure that finally the equipment passes the dimensional requirements, it passes all the design code standards requirements, and there should not be any distortion, whether it is angular as it is shown here, which is a very common defect what we see it in the long sims. Bowing, which is also another common defect. The diameter at the two ends of the shell you will see suddenly going up, and the diameter in the center of the weld or the center of the shell is less. The longitudinal shrinkage or the transverse shrinkage, these are all the defects which, by using a proper technique, proper fixturing, proper sequencing against the neutral axis, or even sometimes changing the position of the weld and having two operators in 3G position simultaneously welding on each side of the weld, or by heating or cooling or preheating, post-heating, these are all the different techniques by which you can do it. And it doesn't happen only in the butt joints, but you can see here it happens in the fillets also, and how bad the fillets will turn. Both, I mean the vertical rib as well as the base on which you are actually trying to weld rib, both may have distortions, and that is not acceptable at all. So certain means of the using a long simmer or pre-cambers as it is shown here, or using a proper sequencing or stiffening the joints, these are all the techniques which are used But along with the internal defects, these are all the external, the third kind of a defects, which is the operation successful, patient died, you have a good sound weld meeting all NDT parameters, meeting all the strength requirements, meeting all the visual requirements, but it is having a distortion by which the equipment cannot sustain the design loads and the equipment is going to fail. So we have to really take care of both these kinds of defects, and those defects will only ensure that we will be able to make a good equipment. And there are other remedial things which we will be able to take it up. Now let's go little more and understand what happens beyond this weld. What we have seen in this slide is what we have seen in the earlier slides is the typical defects what we see in internal in the weld, but we have not studied what happens to the heat affected zone, because welding engineer's responsibility, as we discussed, has an important role to play, that when you are welding, not only you are taking care of your weld as it is shown here, the parent metal is already taken care, we have taken the graded material, tested material, so this side is not really a worry for a welding engineer, because that's the job of the planners, the procurement agencies, the QC to give us the right material for doing the equipment and joining it. We select a good consumable, so welding engineers, the first job is taken care, he selects right parameters by which we will be able to weld it properly. But this intermediate zone, which is undergoing various heat treatments as it is shown from this iron carbon diagram and from this chart, that at the time of at the center of the weld you have the melting point plus a little higher temperature, 30, 40, 50 degrees superheat for good flowability of that material and ensuring fusion, penetration and other parameters which are required. But at the same time, since it is a metallic material, it has a conduction coefficient of expansion and other associated properties of a particular material, and if we are not able to take care of those properties and manage our heat, manage our cooling, manage our fixturing, to ensure that not only we protect parent metal, we not only protect the weld and get a good weld here, a very thin, maybe from few microns to 2, 3, 4, 5 millimeters, depending upon the thickness and the type of material and the material properties. Like some materials have a good coefficient of expansion, so they will expand, contract to a larger extent. There are some materials which have very low coefficient of expansion. Similarly, thermal conductivity, a good thermal conductivity like aluminum, copper will flow the heat and make the entire surface hot. Like stainless steel and others, those who have a poor conductivity, they will try to accumulate the heat. The mild steel, which is absolutely good in all aspects of these physical parameters, is always good to have a weld on a mild steel, but you don't have mild steel giving you the strength, the corrosion properties and high temperature, low temperature properties. So you select various other alloys, materials by which you need to really take care of this heat affected zone. And the heat affected zone, as you see here in this, the strength and the ductility comes down drastically different in the heat affected zone because of these various heat treatments which this heat affected zone is going to undergo, from the melting point to room temperature, and each of these zone will give different grain size, different grain orientation, and this makes the properties to vary even though the chemical composition is not going to change. And as we go to high strength alloys, you will see sometimes the strength reduction, especially see this point which is below the point of the parent material, and that becomes a real challenge because the strength is reducing, ductility goes up, but in the heat affected zone near to the weld, the ductility comes down even though the strength is going up. So this region is becoming very brittle, this region is becoming very ductile with very low UTS, so it will start yielding faster, And the same thing happens in the mild steel also to a certain extent. This zone which happens in the quenched and temper steel doesn't happen in mild steel, and the strength doesn't come below the strength of the parent metal, but variation is surely there. The high strength or the hardness and the low ductility happens in the mild steel also, and this happens in every alloy, whether it is nickel, copper, titanium, aluminum, and other cobalt based alloys. Heat affected zone is unavoidable, and we need to take care of it. So in summary, for this particular topic, I am saying that defects are internal, defects are within weld, defects are external to the weld, visual defects are there, NDT detected defects are there, which are hidden, which are inside the weld. The defects which are coming because of poor setup, defects which are coming up because of the poor fixturing, or not using a neutral axis, or balancing the weld, or not using a proper technique like step back technique, we will land up into distortion or deformation or some mismatch, shrinkage. So all such defects are to be taken care while welding, and our different videos are trying to get us into different aspects of our welding, but those are required to be taken care. And I'm sure, like the other videos, you like this video on the defects. It's a very quick 20-25 minutes video, but will give you a good understanding of various defects, and more than defects, the overall weld efficiency, weld joint efficiency, how are we going to do it, the distortion, shrinkage, other defects in the welding are also not acceptable, and that's the responsibility of a welding engineer or a planner to really look into. So thank you very much for this particular small video, and hope to get your comments on it. Thank you. Hi friends, we are going to discuss in this slide about the Welder's Performance Qualification Record, WPQ or WPQR. This is based on our earlier discussions on WPS and PQR. This is the third step, where after having specified what we intend to do, after having proved that what we intend to do meets the required physical properties for the weld, and also to an extent it gives a confidence about meeting the non-destructive test results. These both are very critical and important for any part or equipment. So the first step is always to prove that the parameters what we are choosing, the consumables what we are choosing, the other parameters like edge preparation and pre-heat, post-heat, if there is any heat treatment, and subsequent to that, whatever is the intended use of this particular weld, does it meet the designer's expectations? So that is proved in the PQR. Now the next stage is that we are not going to have all joints in the similar way, whatever way the WPS and the PQR has been qualified. There will be some variations like position, there will be some variations like the joint geometry, there will be some variations like there could be some additional restraints, constraints, accessibility. So all that has to be demonstrated, and in addition to that, the ideal conditions what we can maintain on PQR as specified in WPS, the root gap, root face, included angle, set in, set on nozzles, or pipe to pipe, tube to tube sheet, whichever way, or any other fillet, the setups which are going to come, the constraints and the difficulties or the practicability of the joint is going to come when we are going to start the equipment. Now the welder should be comfortable and he should be having a confidence that in the given position or in the given setup where there could be a possibility of a little lower root gap or a little larger, wider root gap, included angle may be sharper or may be very wide, we'll have to somewhere butter it, or we'll have to do the overlay kind of a welding. Different nozzles, they have reinforcement pads, and you have a flange on the nozzle, so that flange may be obstructing his accessibility, view, access for the torch. The position which he is going to weld may be a 1 meter high, 3 meter high, 10 meter high, or it could be a very large bridge, tower, column where he has to go make himself comfortable, even though it is going to be the most preferred position of the welding, 1G or 3G or 2G, but sheer the height at which he is going to work, or there could be conditions which are not very favorable like we have in the shop floor or in our training center. So all these are required to be covered in our WPQ. So we'll be first talking about the WPQ as it comes, like a unique number. So there is a unique number as you see it here in the WPQR. The welder's name is essential to be written, the date of welding, the WPS followed, specification of the base metal used, it conforms to which P number, has to be also addressed and written down there, as you will see it little later. And the table here we will be putting all the actual values. These are all what is specified. Every welder has its unique stamp, which is supposed to hard stamp it after every 1 meter or near T joints or near the center of the long seams, depending upon the good engineering practice followed by the fabrication shop. Now the depth of this stamp and the size of this stamp, everything has to be within the code permissible limits. If that is not possible, you can engrave it. If that is also not allowed for some reason, then you will have to put a physical record on a paper, and even after stamp also you need to put a physical record, the welder's photograph for ease of identification, and the date on which this particular WPQ is being released or approved and qualified. So then comes the thickness, type of the test coupon, whether it is a fillet, butt joint, tube to tube sheet, and what kind of a production weld it is going to represent, that we'll have to write it. Expected minimum root gap, maximum root gap angle. If it is a TKY kind of a structural welding, then what is the included angle to which this particular truss or the the shade has been designed, and accordingly we'll have to bring those production weld details also. Good to refer production drawing so that we can see all the joints there. Most of the good fabricators identify each joint like W1, W2 or F1, F2 for fillets, or N1, N2 for nozzles, O1, O2 for overlays, whichever nomenclature you want to follow. You can mention that this WPS or PQR or WPQR is qualifying to which production welds in that drawing. Then the next essential thing is the welding processes. You may have used 2 or 3 different processes like root run by TIG welding, subsequent runs by MIG MAG, or you may have a combination of TIG and then you have plasma, or plasma and the TIG, and then MIG and electrode, and different combinations. So all processes are required to be listed down. You can make additional columns, and whatever is the actual value of that weld metal, what is deposited in that. If you have deposited 3 millimeters of TIG root run, then find out as per section 2C what is the range qualified for. You may qualify for a 30 millimeter plate. That means it will be half of the thickness to 2T, so 15 millimeters to 60 millimeters. But in that, how much TIG welding you can do it, because you have done in your WPQ TIG welding of 3 millimeters, 5 millimeters. There could be some limitations. All those are required to be studied, and the range or the actual values are required to be rightly specified. You have to do the physical measurement and then write it down so that there are no confusions. Similarly, the backup. All these we have discussed in WPS, so I am not going to repeat and add more onto it. So we can increase the thickness, range, or the weld metal deposited, and the backing details, whether it is metallic backing, it is weld metal backing, or is it, that means welding over welding, or is it the weld metal which is back chipped and re-welded. So the second side, when you are welding, it is having the first run as your weld backup, and then double welded. That means you have single V or double V, and sometimes you use ceramic backing or a copper backing or aluminum backing or a stainless steel backing for aluminum. So any material combination of the backing you are using it, you can highlight it there. There could be a So once you cover your backing material details, then the plate thickness, that also the actual, and what is the range qualified. Pipe diameter wise, if it is there, the range you have to give the diameter and the pipe thickness, both are required to be specified. Base material P number, S number, that needs to be given. Filler wire, once again F number, SFA number. Consumables, whatever inserts, if you have used, normally in TIG and plasma we use inserts, so we give the insert qualifies to which SFA number. It has to be near equivalent to the filler metal only. If we are using flux cord wire, what kind of a flux, what is the specification. If it is a submerged arc, what is the specification of the submerged arc. Is it powder, is it the coarse, what was the grain size of the flux, and then the deposited thickness of the weld in each of the process, as we discussed earlier, is required to be listed down. I think most important point here for the welder is the diameter of the filler wire, the diameter of the tungsten, ceramic. Those are also required to be listed down. If there is a trailing shield, we need to list it down. If we have activated flux, if there are any metal additions through the flux in electrode, then that has to be synthetic electrode or the pure original electrode with only fluxing agents on top of the coating. So these are all the factors which decides the coating factor and the way the welder has really maneuvered and the accessibility issue he has seen it. If you have used a very thin electrode which is non-synthetic, and then you are using a synthetic electrode, your deposition may be higher, your diameter will be higher, and then accessibility, the visibility of the weld comes into a picture. So we have to be careful, like WPS, PQR. If you don't want to show it on your record and submit it to third party, once again, no issues, write down whatever bare minimum here, but for your internal records you must have annexures 1, 2, 3, whatever annexures you want to do it, and please mention those annexures here in your the document number, that it has so many attachments. Attachments need not be given because that is our IP. So even if you make a mention in this, there is no need for us to submit it to the third party inspector. Let's go to the second page of the PQR, the welder's performance qualification. And next is the deposited thickness for each of the process. The welding position, as we discussed earlier, once again very critical. Take a photograph of this position in which you have done it. If it is 1G, whether welder was keeping the plate, WPQ plate, PQR plate on a table, or he was sitting down, or whether he was standing and then you have given him, or was it really put onto a rotator and you made that pipe to rotate. So good to have these details also for 1G, 2G or whatever positions, if it is vertical, uphill or downhill. These are all essential variables which are required to be noted down. A welder qualified for downhill is not qualified for uphill, and so the vice versa. So it is good to record everything. Inert gas backing, we discussed it earlier, whether it is argon plus helium or any other combination, short circuit, pulse, globular, spray, synergic, all those different modes. Each mode is very, very specific for a welder to have a comfort and training in these processes. Then the type of current, especially in GTAW, it plays very important, and especially if you are using AC or DC, then the modern machines give the variable polarity possibilities. That means you can adjust your positive, negative in DC, and AC also you can have a square wave where you can still maintain what is the positive and the negative percentage in that particular cycle. The frequency of the output, that also is good to record, which is not given in the format, but good machines will give you what's the frequency of the output, and the frequency makes a huge comfort. Today the welders are very fortunate that they don't have to do using a very traditional contemporary machines, and the electronics in the machines is giving a huge flexibility to the welder to improve his performance. And then comes the non-destructive testing results which are required as per the data, and good to once again attach the report of ultrasonic or the liquid penetrant or any visual inspection. You have to be very carefully do it. The reinforcement has to be measured, penetration has to be measured, the ripples, if you can count per centimeter or per 10 centimeters, you can record it. Undercuts, crater cracks, crater fill up, these are all not the points which are recorded here on the WPQR format, but good to have a separate sheet to record this. If it is a fillet, what's the fillet size we got, was it equal, unequal, how many runs it has been achieved, after each run what was the fillet size, if you want to record that, so that how the bead placement has happened, that will come to know. In the butt joint we should write down the number of passes, number of layers, and then the guided bend test. For a welder qualification we don't do the tensile, but guided bend test gives a very fine sidewall fusion which can be missed out in ultrasound or in x-rays radiography, but you will get it if it is the bend test is correctly conducted. The sidewall fusion and effect of undercuts, the penetration side fusion, all those things are so important for a welder qualification that you need to really do a good bend test as per QW 160 of section 2C, and that gives the former dia what is the minimum width of the bent specimen, what is the thickness to be taken, and then like in the previous WPS PQR, who conducted it, which lab certificate, the welding supervisor's stamp, whether has he witnessed all the joints, or whether he has been recording the parameters, is there IoTs or any other SCADA systems on the machines which can be used to record it, especially if it is a orbital weldings, that gives a printout data that can be taken and added to this WPQR format. And this is the way make the format richer and richer in such a way that when you are going to go from a simple test coupon to the actual job, all the variations on the actual job, you need to map it down to the WPQ and see whether welder has been exposed to that kind of a condition. If he is not, good to give a small mock-up and get a test conducted, at least the NDT and bend test if we can do it, but NDT surely we must do it, and then allow welder to go on the actual job. So even though there are very minimum requirements which are listed down by the code, for a fabricator we have to expand our WPS, PQR, WPQ to write down as many details, and to ensure that when we are going, just having a simple qualified procedure or a WPQR doesn't mean that on the job you are going to give a good performance. Maybe over a period of time the confidence and the repeatability of the jobs will give us confidence, but till the time it is good to do a systematic approach. And even if we have a practice, there is no substitute to mock-up. The cost of repair on the actual job and the delays associated with it, and if it is under the third party, getting their approvals and permissions and their doubts, it's so tedious. I think we can easily afford to bring a small mock-up, get it welded. Even if there is a delay of 1 or 2 days, I am sure you will be saving in weeks and months, and a huge cost in case it gets into. So prevention is surely far better in welding, as rework is very expensive. It is not like a mechanical joint where you unscrew, replace gasket or replace o-ring or replace bearing or refit and retighten it. It is not as simple as that, because it is associated with heat. It has its own heat affected zone. It has its impact on the metallurgical characteristics, on the grain growth or any other dendritic growth which are anchored. The distortions are very high, so even if you are successfully able to repair it, the distortion will kill your job for not meeting the dimensions. And that is where I have stressed in each of these 3 documents, which are taken as very simple, and just quickly it is being done and announced that we have done all the necessary work now, and we don't have to really worry about it. So don't really engage into this kind of a shortcuts when it comes to welding. Even if it is a simple carbon steel welding, please do mock-ups, please do a thorough WPS, PQR, WPQR qualifications. Gain confidence, you will enjoy your job when it is on the shop floor, and you will deliver it on time. I hope these 3 sessions of WPS, PQR and WPQR brought in more insights into welding and associated fabrication risk and the mitigation plans. And prevention is the best, the remedy before we land up into resources. I hope you will enjoy it. Enjoy welding. It's a beautiful a profession where we are joining 2 metals, when we are making progress on the job physically. By machining you are taking away material, by setting up you are only bringing it together, but the actual welding, making a job to progress and to sustain it for its lifetime, is the job what we are doing as a welding engineers. So take a pride and be happy. Thank you. Hello friends. So today we will be discussing about welding machines. I think we are now nearing to the last few topics of welding. It's a big series of lectures or a big series of videos which I made on welding. So this is one of the last the episode or the last video on this, and we'll be talking about welding machines. As you know that there are many welding processes, and each welding process requires its specialized kind of a welding machine, and we'll study how these welding machines are designed, what are the voltage current characteristics it can give, and because of that how we can make different kinds of welds very successfully using different processes and different parameters or the features available on the latest welding electronically controlled machines. So let's start our journey from the welding machines. As you see here in this particular slide, there are more than 15 types of welding machines. We have taken only few of them here. We start with the transformer, the basic transformer, which is it's AC only. Only thing we use 230 volts or 415 volts and bring it down to open circuit voltage of about 60 to 80 and arc voltage of around 20 volts. So that's the first, just a very simple transformer machine which is used in previous years. Now I don't think even a very small grill manufacturer uses a transformer, as single phase rectifiers are available very cheap and they are electronically controlled, maintained, so their output is far better than the transformer. But that's the way the welding started. And then we have the another kind of a welder which is a spot welder. One is the resistance welding, other is where we use the resistance between the two plates and pass a high current, so that becomes a spot welding or a seam welding or a stud welding kind of arrangements. And later on, as we found that instead of AC, DC is a better source, we moved from transformer to thyristorized machines. These are once again very simple rectification using diodes or thyristors, and converting three-phase AC into three-phase DC and superimposing that to get better ripple factors. Less ripple factors in welding machine gives a pure DC and gives lots of advantages. There are some combinations like the transformer. If you want to use AC for aluminum TIG welding, you can use it, or for certain electrode 6013 you don't want to use DC, you want to use AC, then transformer is available. The same machine has a combination of the transformer and the thyristor, and that gives a rectification, so you can either choose a DC or AC. It's a straight simple machine where you set your only current, that's the only variable which you are able to adjust. Voltage is automatically set because of the transformer ratio. The rectifier or the thyristor also has basic step down by transformer, and subsequently it gets rectified, or the AC gets converted to DC. We also use oxyacetylene welder. It's not electric, but there you use a fuel and oxygen, and fuel is normally acetylene, but many times we use LPG, CNG and other types of gases also as a fuel. Create a flame burning the fuel with the oxygen, and adjust the temperature, the flame width, height, dimensions, and depending upon the thickness of the plate and the filler wire, you can select the type of flame and the intensity of the flame. So from these three basic machines, a series of machines have been developed. Like you see the SMAW machine. Now this is a fully electronic controlled, where you have a possibility to select voltage also. Then we have a classical rectifier which has some remote controls, like you have a remote pendant, or you have a remote the foot switch. Depending upon the type of foot switch, you can adjust the current also, or you can start stop the machine. Then came from the stick electrodes to the continuous wire, the MIG welders, the submerged arc welders. Now these processes are different, and therefore we will require a different type of power source, which we'll study it in the subsequent slides. But what happens is, in continuous wire, you need to adjust your arc length automatically, as you will be looking through, or you will be feeding the wire continuously, and very few machines offer the variation in the wire also, and it is difficult also for a welder to really select the wire feed and current separately. As you increase wire feed, current increases, or vice versa. When you increase current, wire feed also increases. So in such cases, you require different characteristics between voltage and current, and you try to use as flat voltage characteristics as possible, whereas in the electrode welding or the TIG welding, you try to use drooping, that is, voltage drops substantially as you change your arc length, and accordingly your current gets adjusted and current is maintained almost constant. So variation, while manual welding, you still get uniform current, and that's the advantage which we try to really explore out of this kind of welding characteristics. Now, before going to the welding characteristics, let us see how it gets connected. I mean, you know the welding power source. Either you can connect a holder, earthing clamps, various cylinders. Then whenever the most advanced electronic machines are there, they will have a data acquisition. That means what is happening on the voltage and current, and accordingly they will adjust it. You also have a control over the wire feed, and many of these machines in today's automation and robotics world are PC controlled, so that like a CNC machine, it gives the output. So these are the various welding types of welding machines and their usage connections just now we saw. Now let's move on to the very important topic of how the welding characteristics gets decided based on the voltage current characteristics, or the voltage current chart or a graph. We'll see it in the next slide. As you see here, there are two types of graphs what we see. First is where the current is almost remaining constant for the variation in the voltage or the arc length, and that's why the machine gives a drooping characteristics. That means the voltage drops as we try to change the current, or there is a variation in our arc length. And whereas the other one is where voltage is almost flat, the open circuit voltage to arc voltage, there is hardly not much of a difference. Like here, the open circuit voltage will be 60 to 80, arc voltage will be about 20-25, and the current within this range of voltage, since it is almost tending to a straight line, it is remaining same. That means a variation in the arc length, the delta V here, the delta A is negligible. But if we go to the other characteristics which is shown here, is where we get a substantial change when there is a variation in the arc length into the current also, and accordingly if the current increases, the wire will melt more. If the current reduces, wire will melt less, and if the wire melt more, the arc length increases. If the wire melt less, the arc length reduces, because wire feed to both of these is going to be the constant, and that's the advantage which we try to take by having a flat characteristics or a drooping characteristics as indicated in these two charts here. However, sometimes it is ideal to have both the characteristics in the same machine, and such machines are now available. You need to make some arrangements in the switches and the electrical connections. Instead of only positive negative, there are additional ports which are given to be selected or connected, and then you can change it. Similarly, by trigger, you can change from drooping characteristics to a flat characteristics, and such advantages are now available in the latest welding machines. So it's very important to select a welding machine with the right characteristics that suits best for your processes and for your application and the type of material, joints, and the position in which you are welding. You will see some more variations in current which are possible other than the voltage current characteristics. Just purely looking at the current, how it can be played and made. And as you see here in this, the constant current output slope is some jobs requires a steep volt amperage curve, whereas some requires a less steep, and where we take a range of the voltage here is about 27, the amperage set is 125, and depending upon the variation in the characteristics of the machine, as you see here in the drooping characteristics and in the flat characteristics, the variation can be up to 15 amps or to 100 amps, and that is something which helps in either maintaining the constantly fade wire arc length, or electrode where we are going to move the torch holder or the electrode holder uh, downwards as well as forward in the direction of the welding. So let's move to the current characteristics. Now you see here our fundamental AC, the transformer gives output like this: sinusoidal wave, 50% plus, 50% minus, and changes 50 to 60 times in a second. Very fast changeovers. You cannot see it by eye whether it is positive or negative, but it demonstrates onto the welding characteristics. When you put a rectifier, a thyristor, or the latest electronic controls, the sinusoidal wave gets converted to a flat DC, positive and negative here at the bottom, which is not shown in the chart. And that's the way even the generators also in the previous days used to work and directly produce a fat characteristics. However, as you see here in this, the characteristics, even though there is a rectification, that means if I use three such waves, the RYB, red, yellow and blue, and superimpose, and then when it comes from the positive, let's say about 2% of the wave gets rectified and non-rectified, and up down happens, and electronic controls nowadays have rectification which is nearing to almost 100%. 0.2 ripple factor is the best machine so far I have seen, and supposed to be giving almost pure DC. However, even 100% DC rectification is also possible now. So this is one important characteristics of the current. From a sinusoidal wave, we convert that into almost flat DC, or up to 2%. Most of the welding processes accept the ripple factors, and that is easily possible using a very old thyristor or a bridge rectifier technology, or electronically nowadays it is possible to do it even at better than the 0.2% ripple factor. Similarly, what we are using here or converting here is the same 50 or 60 cycles per second. That is the 50 hertz frequency of our electrical systems. But now with the electronic controls, this frequency can be increased, and many times it is very helpful, and you really make the pulses, instead of 1/50th second one pulse is getting completed, or a rectified wave gets corrected or completed, you can make it to 2 kilohertz, 5 kilohertz, 10 kilohertz, whatever frequency your rectification can take it through electronic control is nowadays available, and that helps in really stabilizing and making ripple factors to almost zero. Plus this higher frequency also helps in improving the arc force, and that is essential when we are doing the root runs or complex runs where root fusion gets difficulty, where you have one side edge preparation, other side vertical, still it becomes difficult and you can use it. The second advantage with the electronic control is that we are not only able to rectify it, but we are able to modify the sinusoidal pattern to kind of a pattern like what we are seeing it here. It's almost a square wave kind of a pattern what we are getting it, or we can get with little sloping up and down, so that we get good detachment of the weld pool or detachment of a liquid metal from the wire towards the weld pool. Now here the important parameters in this both this kind of pulses is the while the current is pulsing, this is called as a background current, this is called as a peak current or the main current, and between the two the average out depending upon the time of pulse and the time of the background duration gives the mean current. It's not a simple arithmetic average, because duration here is small, you can do exactly reverse. The peak can have a larger duration and the background can have a smaller duration. The whole idea is that the type of material, type of wire, type of process you are using it, we want during each of this pulse one droplet of liquid metal to get detached from the wire and get transferred onto the weld metal. That gives the best welding without spatter, with complete fusion, and the kind of a homogeneity it creates because of the vibrations, or because of the the lamellarity of the weld is destroyed, and you create a very small turbulence, and that turbulence helps in maintaining and retaining the chemistry and avoid segregations if there are alloys which has a higher segregation tendency, plus the fusion becomes very good. So in this slide we saw how from a sinusoidal simple wave to a rectified DC current to a square wave or little sloping wave, and adjustable peak current, peak time, background current, background time, and ensuring that we select the frequency in such a way that for every pulse we get one droplet, and the size of the droplet can also be controlled. It can be as small as possible, so that it will become almost like the continuous flow rather than the discrete flow. However, in the short circuiting method of welding, we use a discrete kind of a welding characteristics or the parameters, and those parameters, let's see now in the next slide how we are able to adjust. So here is the control panel on the left top, as you see, where all these parameters what we want when we want to have a pre-flow, when the welding initial current we want to set at, and then what slope at which we gradually want to increase from the initial current to the final current. The final current has a pulsing, like you see it here, how the pulsing starts, whether the pulsing to start from the upslope or even the initial current, all the features, all the parameters, all these control panels. So from a single uh, adjustment of current today, see how many knobs you have to really adjust and get the best welding characteristics possible. And thanks to this latest electronics and the involvement of electronic engineers in development of welding machines, we are getting such a beautiful characteristics of voltage current characteristics plus pulsing of current to adjust. And there are different types of controls we give, that once you press it, it gives only the gas. Second time you trigger the torch on your TIG or make like a 2T machines or 4T machines, then you get the current also to get to the initial current and upslope and then main current. Once you trigger it, the downslope starts. Another time you trigger it, the current stops and the pre-flow or the post-flow continues till the time the welding requires to be shielded. So this is the way you adjust all your current whichever is required. Now in the next slide I will show you that how these adjustments in currents is helpful to make automation successful. When welder is doing with his torch in his hand and maybe a foot switch or a small knob switch onto the torch, trigger switch onto the torch, he is able to do it. But in automation we are going to operate everything remotely, and if a particular sequence is given, which we will study in the next slide, and probably that will end our this video. So as you see here, we have a pre-flow. After the first, the torch has to be completely flushed, plus the pre-flow is also used not only for flushing the torch but also for creating an atmosphere near where we are going to start the weld, or near the pipe, or inside the pipe if we are going to do a purging, or if we have a backing strips, how we are going to do that back purging. And then after about 6 to 8 seconds normally, but it can be very high, up to 20 to 25 seconds depending upon the volume which requires to be purged, the length of the torch, the purging volume and the purging area. You then start your next the trigger, and that starts getting a small upslope towards the initial current, which is about 1/3 of the final current. And at this stage you check whether all the systems are working well. It's a very small current, doesn't damage the material, and at that stage you actually start your the rotation. That means the movement between the torch and the job, either the job rotates or the torch starts moving, or if it is your orbital welding, the torch inside the tube will start rotating, or the tube will start rotating. And then after stabilizing for another 2-3 seconds, you start the second upslope, which is going to take us to the final current. As we saw in the earlier slide, either we start pulsing right from the zero current itself, or we will start pulsing once we reach to the final value, and then the pulsing starts, continues to the required rotation. And this is the point where actually for a circular seams our 0 point starts. The 0 is not here or not here. So don't make a mistake that just because the job has started rotating here, our 0 has come for the calculation of overlap. The 0 starts at this point when you reach the full current or start pulsing at the full current. Then you go to 360 degrees. Now your actual the overlap will start, that is 7 to 8 degrees of overlap at the same current, the full current. And then you stop your full current and start descending down on your curve to the next level of current, which is normally 2/3. And at this 2/3 current you try to fill up your crater and avoid crater cracks. At this point, when this 2-3 seconds of 2/3 current is stabilized and the craters are filled up, you will then stop your rotation or the movement between the torch and the job. The downslope starts further, comes to 0. This is the point where your post flow is going to start. And since we had the two options, either to start the motion at this point where the downslope is starting, or we can stop the motion at this point where the pre-flow or post-flow is going to start. But for sensitive alloys like titanium and aluminum, it is good to stop motion here, so that you will get purging or the argon atmosphere continuously, or the CO2 atmosphere continuously across the weld or near the crater, and you don't have the oxidation of those areas. And this is the way you continuously move it, and this all the possibilities are explored for every run. You make a separate program right from root run, to the fill up runs and to the cover up passes, and accordingly you are getting for every run, every pass, a different characteristics what you desire between voltage, current, upslope, downslope, pulsing, non-pulsing, frequency, high frequency, low frequency, and you achieve the best weld. So a little study of the joint, making sure that for every run you have already pre-programmed the machine if programmability is available, or you can select the right knob positions. You can make a chart for each of this pass, what is the setting in each of those knobs you want to keep it, and then hand over that sheet to the welder and ensure that he follows it. Today's IoT or the SCADA systems, as we saw earlier, where you can find whether whatever settings you have desired you are getting it, or input voltage conditions or input conditions are changing your output to some extent, and that needs auto correction. So you can then have a CNC or a PC control machine, so that when the SCADA gives you input or output, it gets further improved onto the welding facilities. So I hope this episode on the welding machines and the various characteristics of voltage, current, and the possibilities of the current itself, how we can move, change, vary to the best advantage of ours to get the best welding. And as you see here in this chart, how the welding, it starts very small thin welding, goes to the wide whatever is required, and once again goes to a thin welding. And these two areas are not the overlap areas. From here to here, the overlap area comes from this to this, and you achieve a uniform. You really find it difficult in the latest machines to see where you are actually started and where you ended, if the welder and the automation and the programming of the machines and the machine's capability to deliver as programmed is the best. So thank you very much for going through this episode also. And if you have any suggestions on what more topics I should cover, you can send me on Facebook, LinkedIn, and I will try to do justice to your suggestion. Thank you very much for listening to the series of welding topics. I enjoyed, I also learned while making these videos, and let's do all our welding engineers and welding practices as India, as a shining Atma Bharat India, a very successful, and build all our equipments to the final satisfaction of the customer. Thank you so much. Dhanyawad. Jai Hind. Hi friends. I thought that I finished all the sessions or the topics which I wanted to cover, but thank you very much to those who have gone through my videos and given me a suggestion that I should make one more video on the different kinds of welding accessories or the machines which are available for doing different things in welding, as welding has infinite possibilities, and the way we look at it and the way we think of automation only has a limitation. Once you are able to imagine, I'm sure you will be able to get the accessory or attachment by which you can either improve your quality, your productivity, accessibility, or where you are required to weld in the very very restricted areas, or you may have to do it remotely. So once again I am thanking for giving me this suggestion. I completely missed out on this topic and this aspect of welding, but it's important to consider in today's modern world of automation, and making something impossible possible is what we as a welding engineers are always attempting. Not only materials, but the type of joints and the type of NDT requirements and the properties which are demanded on the welding. I think these machines, the accessories what I'm going to explain in the next few slides, will be of very much interest to you and will help you in improving one of the quality cost delivery requirements. And let's make a journey on to this next topic. So even though the last video was supposed to be the last in the series, I think I am going to get many more suggestions, and this I don't say that once again as the last. The series will continue. More and more suggestions, more and more discussions happening, more and more challenges we are going to encounter. I think more and more videos on welding to make really a welding a very popular engineering process that makes it two materials to join together and keep them binding for lifelong. So let's start our journey on this. So first let us see the welding viewers. One of the requirements in welding is to not only keep on doing the string welding, that is straight welding without doing any weavings, but many times you are required to weave your weld torch or your weld electrode in such a way that you cover the maximum area without hampering onto the welding properties. This helps in faster deposition. It gives a beautiful finish. But while you weld or while you weave, depending upon the joint, you need to follow different patterns as given here. Now, these patterns are not easy to follow unless you are highly skilled and practiced, not only having a skill and understanding knowledge, but you need to really practice it well. And the important point here is that the spacing between, or the pitch as we call in our screw, so the pitch of this and the dwell, that is how much time you are going to wait at the extreme ends when you are going to weave it like this. So here, as the diagram shows, he is going to take, instead of weaving, a small turn and come back here. Once again here a small turn and come back, again a turn and come back, like that he is going to do it. Here there is no much of a dwell, probably the joint doesn't call for that kind of a weld, and the weld has a good spread, the parameters of voltage current are good. So even if you quickly move from one end to other end, and normally we do this 2 to 3 times of the diameter of the wire, or 2 to 3 times the coverage what a stringer bead will give, or it can be 2 to 3 times your ceramic nozzle, depending upon what kind of a material you are using. So you don't require, if the parameters are good, no dwelling. Like here you see a dwelling only on one side, other side there is no dwelling. This here there is no dwelling, but very fast and zigzag going up and down. Here it is going only in forward direction, here it comes back also, and this is kind of a square, and this is another kind of a variation which is there, which is coming up. And you need to have, as I said, minimum 2 or 3 parameters to be controlled. One is that what is the motion you want to get it, so your controller should be capable of designing this kind of a path for your torch through one of these means which are used as a weld weavers, or nowadays on the robots you can plan it on the robo itself for the weaving attachments, or the robo itself will weave and you can do that. And the parameters what you set is what is the width of the weaving you want, what is the pitch you want, what is the dwell time, whether you want on both sides, one side, and so many other variations you can do it, whether you want forward backward, you want a square movement, you want a typical thread movement, and all this is possible on this kind of oscillators or on the controllers. So having such attachment along with your welding sets will help you in perfecting the automatic welding and bring it as close as the human or a welder himself when he is going to see and weld it. Now let's go to the next one. In this slide we are seeing manipulators. So when you are actually going to do a welding, you require a motion between the welding head, welding torch, and the parts to be welded. Unless one of them is going to move, you are not going to get the weld successfully. So here we are showing that the jobs are either moved on rotators like this. There are number of types of rotators which are available there. I have picked up only one for giving you an idea. You can Google it and get more details on what kind of rotators are available. Similarly, the column and boom, where you have a column and a boom and the welding head is attached here on the top of it, and then you move it. And when you want to have a distant kind of attachment, or when you want to change the angle of your joint, you need to use this kind of a positioners on which you will mount your job and then rotate it. And then there are nozzle welders which actually go and sit on top of the nozzle, and then they will weld your applications. And there is a track and the trolley arrangement, where you mount this track on the job and the trolley moves across in 5G position. Here the jobs are going to be converted into 1G, 2G or 3G, which is your most preferred and favorite condition in which you are going to weld it. So there are lots of manipulators available. It's almost becoming like a machining process, and you have different kinds of machines which are available along with the welding machines. The basic power source, like in any machining process, you have a spindle, whether you are turning it or you are boring it, milling it, you must have a spindle, and then the manipulators to move the job to create relative movement between the spindle and the job. So similarly, a relative movement between a welding head and the parts to be welded is required to be achieved. Let's move to the next one. Okay, so in this slide we are seeing various kinds of torches attachments which are available for going inside a very small diameter pipe, tubes, or a constricted area, where your torch has to go within a bore, or it has to go within a pipe and do either a welding, a butt joint, fillet joint, or a overlay. You need to really deposit weld as it is shown here. So you need to take an extended length of a torch plus a wire feeding attachment that will go towards the end of it, and the whole thing has to really work with very limited access or no access based on your setting, as we do a boring inside machining operation, where you don't come to know what is the finish you are getting, whether everything is going on well, and all your settings are adjusted from the external the parameters or the knobs what you have on the machine. And in CNC machines it becomes easy. So similarly, today the advanced controls, AVCs and other attachments which we have seen in the earlier slide helps you to make it almost a perfect kind of a joint inside a constructed area. So that's the advantage what you use it in this kind of a construction. In this slide we are talking about the seam tracker. If you are doing automation, the welder is able to see where is the edge and how the welding is progressing. But depending upon your welding edge preparation, you choose one of the a point which is not going to really change in the entire 360 degree, or from left to right, or from top to bottom, and you position your sensor like you see here. And there are many types of sensors, non-contact, contact type, or even physically you can put a small pointer and keep on looking at the pointer, how it is behaving, whether there is a drag in the positioner rotators, or there is a movement between the job and the welding head, not the desired movement in the right direction, but the non-desired. Suppose you are moving in X direction, the welding, the Y direction movement in the joint is harmful, or similarly Y you are welding, X direction is harmful, or if it is a three-dimensional, then X, Y, Z, all three will come into a picture. And therefore locating a joint correctly and positioning your torch with respect to the edge of the joint or any other edge what you are creating will ensure, like you see here, when you have a kind of a butt joint, square butt joint, you don't have that kind of a edge where you can really focus, and many times this the gap between the two you will not be able to decipher. But when you have a good fillet kind of a joint, where you can see this very correctly, because there is a change in angle here of the planes, and when you have a edge preparation, once again you can see it, you can take reference of either this edge. Or just for the completeness of our presentation, I am adding this additional slide. As you see in the previous rotators, we had a different construction. Here you have kind of a Caesar lift kind of arrangement. You have two rotators which are connected to each other, and you can adjust various diameters. You can adjust the length or the width between the gap between the two positioners or the rotators, and accordingly you can stop the movement, ensure that whatever OLT is there, it is taken care. To improve weld efficiency, the deposition efficiency, not only use a single wire, you can actually use two wires in tandem mode or the twin wires and improve your deposition. And similarly you can do schematically that two separate power sources, or it can be one single power source feeding to both the guns, and both the guns can be independently operated, so that along a fillet you can have simultaneously both the welding going on together, or from both sides if you want to do it, you can do it together, and improve your weld efficiency, weld deposition, and improve the productivity. This is another way of improving the productivity in TIG welding. If you are feeding wire with hand, it becomes a limitation. Manually you cannot really feed it very fast. The larger diameter wires or very thin wires are difficult to feed. The ideal wire to feed with manual welding is 1.6 or 2 or 2.4, but if you have a smaller wire, or if you have a thicker wire 1.2, 0.8, or you have a wire like 4 or a twisted wire, it becomes difficult to feed. And then you use attachment on the torch with a wire feeder like a MIG welding, and bring that wire through a tip, a nozzle similar to the contact tip of our MIG welding, and bring it, adjust it to the right position on the torch, like the welder is himself adjusting where he wants the wire to be fed. So you locate that same point and then run it on automation. The other way of improving the productivity, which is still faster, which uses this kind of attachment and also has a wire which is preheated. It is called as a hot wire TIG welding. So you have another power source or the same power source with the different tappings, and before you feed, there is a small resistance of the wire itself is used, and you give two different connections. So this is a main TIG wire TIG welding power source which goes to the torch, whereas as you see here, the hot wire power source goes directly to the contact tip and to the base material, and when the current passes through this wire, it is not actually creating an arc because the voltage is very low, but the current what we pass, like a seam welding, spot welding, is very high, and that actually gets the wire heated up. The wire gets heated up to even 200, 300, 400 degrees centigrade, and this 200, 300 degree increase in wire temperature helps in much faster deposition, because that much of heat from the welding torch is not required. As your wire is heated, it melts faster, and you can deposit with good uniformity and improve your weld deposition efficiency. This is a unique technique. We have used even the manual as well as the automated double operator technique, where you weld from both sides of the weld together. Simultaneously you weld it. Like the fillet, you have both sides of the welding, or the TSR, the tray support rings, or other attachments which are there on the shell either inside or outside, and you don't want any distortion. So good to weld both sides together. There is a little trick in this. You need to adjust your current, and one has to be having a little lag in the progress. Current and voltage can be equal, similar, or that also can be more or less. You can adjust it, but the trick is to not have at the same point both the arcs, but have a little shift. Little shift means literally 1 to 2 millimeters shift only in the arc from both sides. The first welder is welding. Before his welding is cooling on the penetration side, the other welder's action should start, and he should start remelting that penetration with the additional wire, so that the deposition happens from both ends. And this is how you can improve your the efficiency to a great extent, and control your distortion, which is one of the important aspects in welding to be controlled. The last in this series is the tubes or the tube to tube sheet. That's another kind of a joint which is extensively used in our heat exchangers and other wherever you have heat and mass transfer. So you require very uniform welding between tube and tube sheet, and the difference in thickness, as you see here in this diameter, whatever type of tube to tube sheet joint is there, your tube is going to be between 1 to 3 millimeter thickness, and the tube sheet is invariably 40 plus. So when you are going to melt at the edge only on the top of it, and some of the joints they require even the tube welding at the other end. So when you are welding onto the other end of the tube sheet, which is the tube going straight through the tube hole and gets attached to the other side of the tube sheet, it becomes impossible for manual welding, because you cannot see the diameters of the tubes are between 19 millimeters or even smaller, sometimes to 12 millimeters also, and goes to maximum of 2 inches, that is 50 millimeters or 55 millimeters. But in such cases, to weld it, you must have a good automated system like this. It is called as an orbital welder or a tube to tube sheet welder. And sometimes you have joints where you have a lot of bends in this, as you see here, a bend, and you still have to have a very compact head sitting on top of the pipe, which can go, otherwise manually to go on the inside and see and have that kind of access for the welding becomes difficult. And when you have very sensitive tubes, like in case of semiconductors or your food and beverages, you cannot have a penetration, so you need to control your internal purging pressure as well as the closed loop or the closed system orbital welders or open system orbital welders. What I have shown here, they are all closed type of a system where there is no separate ceramic, but the torch is only kind of a TIG torch holder. That means a socket where you put your tungsten, and the entire thing, the collets are required to suit the diameter, and the collet completely closes any gap between pipe OD and the chamber, and the gas is purged into it with very beautiful controls, which has 999 sectors, and every sector you can have a separate program. Similarly in this orbital welder tube to tube sheet and this tube to tube or pipe to pipe welder. So there are a lot of means available today, as I explained in this short video, but it is going to be of significant improvements you can really get in your quality, productivity, and your deliveries will be much faster. So make use of such accessories, attachments which are available, and learn how to really select the right accessory for you and deploy it in your day-to-day welding, or wherever you have this kind of constrictions, accessibility, uniformity. So these are the ways you can really improve upon it. So thank you again for getting into this one more video and watching it. Please keep on sending feedback so that I can improve and add more into our list to make, as I said in the first beginning itself, that let's make this welding a exciting business, exciting profession, and we all should go and work really like a heroes. We are finally joining the metal, we are making the job to progress. In machining, you actually are trying to remove unwanted material. Here we are actually getting together two pieces and making a joint. So our role is very critical, important in the progress of the job, and if we do it first time right, I think we achieved what we want to actually desire or we want to aim for it. Thank you again. End of the tube sheets.